helped us prevent this. Well, not prevent, but like see that nothing actually happened. So the Finnish contribution is mainly thanks to this instrument, which is the Nordic Optical Telescope on La Palma, with which we made these the majority of these observations. So with that, let's go on. Okay, so what would have happened if 2024 YR4 would have crashed into the Earth? So here are a couple of examples which we can give you an idea, because 2020 YR4 was on the order of around 50 meters, so similar events. The first one on the left, the Tunguska event in 1908, devastated 2,000 square kilometers of forest in Siberia, so that's, if it's a circle, that's 56-kilometer diameter circle. The burst was in the air, so large area destroyed. The other similar event, which could have happened, the meteor crater in Arizona, 1.2 kilometers across, 200 meters deep. So this type of asteroids, this is the impacts we call, the scale is city killer. So that's what would have happened. Not a global disaster, but like a local catastrophe. And where would have it happened? So initial predictions showed that this area marked with red, all the way from Panama, Venezuela, across Africa, Nigeria, Ethiopia, and then India, Bangladesh. So the equatorial areas would have been somewhere there. It would have impacted, and as you know, many populated areas are in this region, so bad things could have happened in this area. So yeah, the ocean is, the ocean covers a lot, but in this particular case, not so much. So as we know, the impact didn't happen. So, but before we go into why, I just wanted to give you an idea what we needed to do in advance to prepare for this event to quite quickly rule out that this didn't actually happen. So for the astrometric measurements, you need sources of error. You need to know them well. So the first one is the first source of error is the position of reference stars. So those of you who had 2 morning coffees perhaps be able to see the small asteroid there. For those of you who don't, it's over here. So this is the 2020 YR4 observations with the knot. So you can see it's quite faint. And then you can always see that all of these reference stars which serve as the reference points for astrometric reductions. So the Gaia satellite, which ended last year, its observations, it's revolutionized the astrometric solution problem. So this shows that with some previous star catalogs, the astrometric positions were not even, so there were errors up to 0.6 arc seconds. The position of known stars with the Gaia satellite is on the level of micro arc seconds, so 1,000 times better than this. And also the proper motion corrections are now much more better than with previous catalogs. Then the second thing that needs to be known is the precision of known telescope position. So previously on La Palma, there are all different telescopes. So what they did for astrometric measurements is they used one position for the entire observatory. But then, after Gaia happened, we realized this is actually the difference between that position and where the telescope actually was around 420 meters. So this became a dominant source of error. So we needed to fix that. And the third thing is the position of measured position and time. So measured position, it relies to things like the seeing. So we know what is the astrometric error of the of the position. This is due to the local seeing, the dome seeing, and the quality of optics and that kind of things, which are excellent for the knot. Here you can see the dark ones are observed with observations of the knot. So the errors are here on the level of 0.1 arcsecond, which is excellent, even for such faint objects. And here you can see that if you look at the dates, this is just before the full moon and right immediately after the full moon. And as you can see in a minute, then the hazard went away around 18th to the 19th of February last year. So these were one of the main contributions to actually rule out the impact hazard. The other thing that needs to be known is the timing error of the telescope. So there were these timing campaigns, and then now we know that the knot clock is on the order of 0.4 seconds. Okay, so all this preparatory work need to be done in order to rule out at the NORP. Then I'll try to explain you the concept of orbit computation in 3 slides, so bear with me. Blue, here you can see, blue are the astrometric observations as a function of time. Okay. Yes, okay, so the extreme values here are like the extreme orbital positions, and as you go in time, this is the extreme values of how the astrometric position spans. So then you get more observations, and then the area shrinks, and then you get this like orbit, and the orbit is an ellipse. So then, first of all of these orientation angles are solved, and in the end, the two different things, the two last things to be solved is the semi-major axis and the position on the ellipse, so the like true anomaly or mean anomaly. So essentially, it collapses to a line of variation, as you saw in the map. So it is somewhere along a line of uncertainty. And so now I can see how this line of uncertainty was shrinking as a function of time. So here you can see the time, and here is the impact probability. Here's the Earth, here's the Moon. And let's take a look at this quickly. So the line of uncertainty went through the Earth and Moon. Here's January 27th. The impact grows all the time until it reaches around 3% here, February 18th. And then it shrinks because additional observations kept on becoming and pushing the solutions away from the Earth. So this is why we first thought it was a hazard, and then it was not anymore. However, currently the impact with the Moon is still not ruled out. It's now at around 4%, and what happens with lunar impacts we will probably hear in the next talk, or at least some of what might happen through that. Yeah. So let's see what that happens. If it will happen, many of satellites may become destroyed, which is unfortunate. But then, us astronomers would think this is kind of cool. But so, okay. What else do we know about this object? So we got a spectrum. No, not we, our colleagues. So it's an S-type, so like a silicate. And then there were observations with a phase function, so the dependence of the phase angle, the angle between the sun, the Earth, and the observer. And there were a couple of observations that the best solution is this yellow and blue one. So we know kind of no, these are like, okay, G and G12. So it's this is the H, which is a proxy for size times darkness, is within 0.2 magnitudes. Yeah, so these are actually not observations which were able to constrain this quite well. And then the work by Eric McLennan, which is still in progress, adding all the light curves and making global solution for pole orientation, and then the phase function and the shape. So this is one of the solutions. It looks like there might be a concavity here, so like a triangular donut with a hole in it. So, but we don't really know. But that's like, this is one of the solution. Okay, so wrapping things up. This was a real case. It was a city killer size asteroid, comparable to Tunguska and Arizona meteor crater event. Had an impact probability of 3.1, which is the higher than Apophis. We hear about Apophis in a while by Joe. And then the Nordic Optical Telescope proved to be a significant role in the global community. So I forgot to tell you that because these errors are like we need several telescopes of similar size because these, although their errors are small, they kind of be a little going pushing one way or the other. So like NOT is one of the maybe 3 telescopes in the world that contributed to that in that size range. So a very significant part. Yeah, so, and there's still a 4% probability of lunar impact on December 22nd, 2032. So let's see what happens. And this is actually one thing to mention, that there are actually worldwide bureaucratic processes for asteroid hazard mitigation that they were triggered for the first time ever. Okay, that's it. Thank you.
Thank you, Grigori. We have excellent time for a few questions. Okay.
Thank you. I wonder, what is the statistical probability of indeed erasing a city with that kind of asteroid with just random sampling around the Earth projection, or how it's calculated? So most of the land is not populated at all, or even filled with water. So these percents are for hitting the planet, not causing damage, right?
Yes, so it was 3% of hitting the planet in this case, but then looking at the map, maybe like what is the populated area? Well, you need to obviously count what is the surface area. I would, in this particular case, the land coverage was larger than, it did not go on the Pacific Ocean side, it went on the other side of the Earth, so that was higher than usual. So that was, yeah. I would say maybe 10% maybe, so 5, 10, so it's like not 0.1, it's not in whole percents maybe, because there are big cities like in India and Nigeria, Ethiopia, so.
So 10% of the 3%.
10% of the 3%, yes, so maybe poor, but still. So it's not like 0.000 something, it's actually may be dangerous.
Okay, any other questions?
Thank you, good point.
I have a very quick question. When can we refine the lunar impact probability?
Well, I've heard rumors that there might be JWST observations happening as like this year. I don't know if they're actuating, but at latest 2028. So it comes to vicinity of the Earth every 4 years.
Okay.
So that's at that point we will be for certain.
Okay. Well, let's thank Grigori. And welcome on stage Mikael Granvik with a topic continuing probably a bit from this. Can the moon be the source of mini-moons? And well, maybe with the lunar impact it could.
Okay, good morning everyone. I'm going to talk about roughly the same topic, not quite this particular thing, but what I'm going to talk about is what you see here on the happening here. So of course this is the moon here, and this is the background or the dark side of the moon, and you have an impact there. And then the question is, what is happening to these fragments? Of course, some of them will fall back on the moon, producing these secondary craters. But then what happens to the rest of the stuff? I would highlight that these slides are prepared by Rob Jeddick, who was also the lead author of the paper that is describing this work. So first, let's start with the definition of what I mean by a mini-moon. So a mini-moon is gravitationally bound to the Earth, and it's orbiting within 3 Hill radii from the Earth. So the orbit that you see in the middle here is the moon itself. So about 12 times that is the distance between the Earth and the moon is 3 Hill radii. So this simulated thing that is orbiting in here and showing you a potential track is well within this number of 3 Hill radii, or distance of 3 Hill radii. It makes at least, a mini-moon makes at least 1 revolution around the Earth and comes within 1 Hill radii, or 4 times the lunar distance, at some time during the capture event. So we've had a couple of these events in the past. 2006 RH120 was the first one. Here's the trajectory for that body. And the first analysis of this body came out in, I think, 2009 or so. So we didn't really know, or people did not believe that this could actually happen. So this was very difficult to convince people that this is indeed happening. And then in 2012, we published a paper that I will shortly come to, showing that it actually happens. And this was the second event then in 2020, which was also captured and proved to be a natural object. So where do these objects then come from? Well, we have shown that they can originate in the main belt. This was a paper that we published in 2012. And in principle, these few examples that we have so far are perfectly explained by this model that we have. So we don't need another source for them, basically. However, has always been the question, could they come from the moon? So could the mini-moons actually be part of the real big moon? And this is, of course, something that we've always said no. I mean, this is such an unlikely event, and it would need so large impact that this is never going to happen, or statistically it's improbable, but we have not shown it. So this work, what I'm presenting here, is the first attempt at showing if the numbers would agree or not. So there is no indication, or we think that there's no indication of, or there are no indications of meteorites from the Giordano Bruno crater on the moon, which is about 4 million years old, and this is why we have written or stated in the past that it's probably not a likely source for mini-moons currently in orbit around the Earth occasionally. So these mini-moons actually spend about 9 months being captured and orbiting the moon. So they're not there, the same mini-moon is not there for a long time, but then a new one is captured and so forth. So at any given time, our model predicts that there should be, I mean, the asteroid belt models suggest that there would be one meter object captured by the Earth-Moon system. But it's a different one, so there's recaptures and releases all the time. For this second mini-moon that was discovered, we got photometry for it, both throughout the visual wavelength, and you can see that it sort of matches with a V-type. So all of these measurements with error bars are the measurements, and what you see in the background are different models or different typical spectra for asteroids. So this should match with a V-type fairly well, but it's also roughly similar to a lunar rock. So there could be an indication that something else than an asteroid would actually be the precursor for this particular body. Then we have Kamoa-Leva, which is not a mini-moon, but it's a quasi-satellite, and it's interesting because its spectrum, again, aligns very nicely with Apollo samples. However, this body is 50 meters in diameter, so it's much larger than anything that you would expect to be temporarily captured or in the quasi-moon orbit, because you need a lot of, or a large impact on the moon to throw out 50-meter-sized ejecta. And indeed, we actually showed in a paper that was published just a couple of weeks ago that the likelihood for Kamoa-Leva to be an asteroid is much larger than it would be sourced in the moon. And then we have others also that are not mini-moons that have been captured. Here's one PT5, which shows, again, a spectrum that doesn't quite align, at least with these types of asteroid spectra. But then again, with lunar samples, there's a reasonable match. So can mini-moons then be from the moon? And basically, the idea is very simple. You have an asteroid or comet slamming into the moon or impacting the moon. It launches material from the surface, and this material goes into a planetocentric or heliocentric orbit. And then if it goes into a heliocentric orbit, it's then recaptured by the Earth eventually. And this is perfectly okay. There's nothing wrong with this model. But the key question is, how often will this happen? And can this explain the captures that we're currently seeing? So I will go through the simulation, and the first thing that I'm going to do is go through the parameters so you get a flavor for what we have accounted for in this model. So we need to first figure out how much material there is ejected from the moon and how in what directions and what so with what speeds, etc. So for this purpose, we have scattered a lot of impact locations around the moon randomly. We look at the moon over a metonic cycle, which is about 19 years when the Earth, moon, and the sun repeats in inertial space. The relative geometry repeats in inertial space. So this is about over 19 years then that we've done this analysis. Then we need impact frequencies and impactor diameters, and these we get from NEO models, where we basically have a prediction for the Earth impact rate, and then we scale it to the moon and get this purple line. We also need an impactor density, and here we assume that there's 75% S-class objects and 25% C-class objects, and then we take their average density and use that as a impactor density. We also need the impactor speeds, and these also come from models that have been calibrated to real events. And then the angle, finally, we assume to be 45 degrees. It's a typical average that we use. We have a surface strength and density for the moon. And then we also need some sort of estimate for the crater diameter to establish the amount of material being ejected. And so here you have a crater diameter and impactor diameter, and there's some sort of scaling. There's multiple different scaling relations, and we use this one from Collins as the nominal one. And then we have also, of course, the crater diameter depends on the speed, and there's differences in which speeds you assume for the impactor. The crater shape determines a lot about how much material there is coming out from the crater, and we use the paraboloidal model and assume that this diameter to depth ratio, or depth to diameter ratio, is 0.2. And then finally, the ejecta size frequency distribution. There has been a lot of measurements of this, but when you look at the numbers, the exponents here in the power laws, we range from minus 2.2 to minus 5.5, so there's a huge difference. And we just take some average value then for this with some uncertainty. And then there's also ejecta speed, size versus speed relationships that are not very well established, but we just use something for these also. Here's another kind of plot for the impactor diameter versus ejecta speed then, and then ejecta diameter versus the cumulative number of ejecta, assuming a speed, but of course the speed, the number of ejecta depends on the speed itself. So this is again fixing the size and looking at what of the impactor and looking at what the ejecta would have for the number of ejecta. Then we have the ejecta sort of velocity vector, and here we assume that the material is launched at an angle of 45 degrees, and it goes in all directions, also azimutally. And then we have finally the speeds that we account for. So more speeds here close to the lunar escape speeds, and then we have this map of different speeds. And then we also need, for the escape speed, we also need then the mass of the moon, or basically the G for the moon. And now when we have all of that, we have launched material from the moon with this model, and then we integrate this with rebound, and we get something like this, where you just continue on integrating these orbits for a long time, and then see where these bodies end up in the end. And now finally to the results. So this is now the ejection speed and capture fraction. So this is a lot of relative numbers. So some fraction of them will be captured immediately on Earth-like or orbits around the Earth. And then some others will be captured later on, depending on what their ejector speeds are. And then again, if you look at the capture durations, then we're talking about 1,000 days. So about 3 years or so being captured in an Earth-like orbit mostly. And when you get to the delayed captures, then they are then closer to what we got also for the mini-moons that originate in the asteroid belt, because they have already been on heliocentric orbits. So they probably behave or randomized to sort of match the asteroidal sources also. And now finally, we get to what we actually wanted to have, the size frequency distribution. And now from this, these are now TBOs, which this is sort of a class that doesn't really, for a dynamicist, it doesn't really mean anything, because it's what we call a temporary bound object. So it just happens to be, on paper, energetically bound to the moon, but it could be on the other side of the sun also. So it doesn't really mean anything per se. But these, the numbers that you get from here are sort of sensible, that there should be at any given time maybe several tens of these objects at the meter class. And then when you scale this down, because this is a superset of the mini-moons, so we can take the mini-moons, and this is now the number that we should compare to the observed values. So you can see here that at any given time there should be like half a dozen of mini-moons in orbit around the Earth. So this would explain what we actually see. So now we have two models, and they both can explain. One, that they come from the asteroid belt, one that they come from the moon. They produce similar numbers. So which one is correct? Well, one thing that I should highlight is the uncertainties. So as you saw, I noted the uncertainties for this model, for this particular model from the moon. And when I plot them here in gray, you will see the problem. And now this is stalled, apparently. No, there we go. So now in gray, I have the uncertainties. And now you can see the problem. So we cannot actually know. There's a range of 9 orders of magnitude uncertainty in this model, because we don't know the cratering or how the cratering actually works, or how what the correct parameters are. So this is, of course, we can of course take the approximate numbers that we know of and look at, okay, how do this uncertainty behave as a function of size? And we can see, for instance, that, okay, it's very unlikely that Kamaleva would be from the moon, for instance, based on just this model. So the conclusions, impacts on the lunar surface can create mini-moons. The model uncertainties basically make these models not very predictive or not very useful, but we can do the opposite, actually. We can take the models themselves, and if we can identify mini-moons as being based on, say, spectra, that these must be from the moon, then we can use the number of those mini-moons that we find to actually constrain what we don't know about the cratering effects. And that would be a huge boon, because then we could apply that to all terrestrial bodies in terms of their cratering rate. We would understand how this actually works. We'd have we would be able to constrain it indirectly. So that's everything I have. Thanks.
Okay, thank you, Mikael. We would have time for one very short question. Okay. Well, but then soon we'll not hear them.
Thank you very much for a very nice talk. Have you observed any mini-moons whose spectra resembles not Apollo basaltic spectra, but lunar highland spectra, as highlands covers more surface area on the moon?
I think they were the spectra for some of these objects that we have that match best the lunar highland soils. Yes, yes, indeed. Yeah.
Okay, that's it for regarding the time, so we must go forward. Thank you, Mikael. We continue with Joe De Martini with predictions for the Apophis 2029 Earth close approach from DEM simulations. Please, Joe.
Hi guys, I'm Joe. I'm working at the University of Helsinki now. I'm going to talk to you guys about my favorite asteroid, Apophis. We got a quick overview of how Apophis was a potentially hazardous object from Grigory's talk here. So I'm going to go into a little bit more detail about its 2029 close approach with the Earth. First, a little bit of background about Apophis. On Friday the 13th of April, 2029, very scary, Apophis will make a close pass at about 1/10 of the lunar distance. It absolutely will miss the Earth. Apophis is going to miss the Earth. It is a close pass, not an impact. We're practically guaranteeing it at this point. For the physical characteristics of the body, it's about 350 meters in diameter. It's a rough approximation. When I talk about this in the US, I say it's a little smaller than the Empire State Building. In Europe, I say it's a little smaller than the Eiffel Tower. So hopefully that gives some perspective. As for its rotation period, it's got this strange tumbling period where it's rotating about its primary axis very slowly and then precessing about that at actually a much faster rate. And so we say it's a tumbling rotation period, or rotational state, where it's sort of in this strange tumbling phase going through space. And its spectrum best matches SQ-type asteroids, which is interesting for people who care about these potential tidal resurfacing that may happen in the close approach. As of now, actually, I shouldn't say potential anymore for Ramses or OSIRIS-APEX if the recent Congress missive is anything to go by. So good news, actual missions, not potential missions. The Ramses mission from the European Space Agency and the OSIRIS-APEX extended mission from OSIRIS-REx, which went to Bennu from NASA. So there will be missions at Apophis. This is great news. Cool. So what might actually happen when Apophis passes close by the Earth here? The first thing that may occur is a change in the rotational state. This is actually the most likely and possibly the most easily observed occurrence. You can see on the left here I've got a plot of forces from a simulation that I'll show later on Apophis as during the tidal encounter. So the perigee happens right about here at about 4.5 hours. And we see the local gravitational force up at the top here for a couple of the particles on the surface of Apophis, and then rotational forces plotted against that. And you can see changes in especially the Euler and slightly in the centrifugal forces on Apophis. That tidal force there is a big one. But this will cause a torque to Apophis. And you can see what can happen in a very violent torquing of an asteroid. You can actually blow material off of the surface. We're not going to pass the local gravity here, so we're not going to blow off any material like in this simulation, but it's just to give an example of what could happen in a more violent rotational change. Another thing that may occur is tidal deformation, so a change in the shape of Apophis. You want to think about squeezing a dodgeball in this case, right? If you tug it along one axis, then it can contract along the other axes, and you get this strange potato shape out of your sphere instead. So again, this is a very violent tidal deformation from a paper that we have in review right now from one of my collaborators. Apophis will not deform this much, and I'll show you exactly how much it will a little bit later in the talk. Last thing, we may get some potential seismic events on Apophis. Here is a violent seismic impact on a regularly packed spherical rubble pile, and you can see these pipes are contacts between particles. So the red means that the contact force is larger, and when the pipe disappears, it means that the contact is momentarily broken. Again, here for Apophis, we're hoping to see some kind of seismicity that's induced by the tidal stretching, that deformation that I showed you on the last slide, and I'll show you just how much we'll see of that in a moment as well. As for the method that we use to study this, we use the parallel n-body gravity tree code PKD-GRAV, which calculates mutual gravity between spherical particles and uses a soft sphere discrete element method to calculate interparticle contact forces. So basically this means that we allow our spherical particles to interpenetrate very slightly at the point of contact with a degree of interpenetration mediated by a restoring Hooke's law spring force. And that can act as a sort of material stiffness akin to a Young's modulus. So we can sort of create a physical, a realistic stiffness for our particles here, or at least for our medium. This soft sphere method allows us to handle energy damping, rolling, twisting, and sliding friction. We can add cohesive forces, all manner of interesting things. And we can mimic shape effects by gluing some of our spheres together into what we call aggregates. These are treated as single particles, so the relative positions of any of the spheres in an aggregate are fixed, but the aggregate itself moves by its center of mass as a sort of single object. Cool. All right. Now into Apophis itself. The two major unknowns about Apophis are the orientation that it will have when it encounters the Earth. Like I said, that tumbling spin state is very difficult to predict, and it's really difficult to propagate forward. Our last best observations have still pretty big uncertainties about the orientation of Apophis at the time of closest approach. So that's going to be one major uncertainty. The other one is its packing distribution. We have a fairly good idea about its shape. We think it has this bilobate structure based on both radar and light curve data. So we're reasonably confident about that. The exact details, maybe less so. You know, we don't know about where all the boulders are on the surface, but Osiris Apex is going to figure that out for us, or Ramses if it gets there first, I suppose. So we're going to try different packing structures and different orientations at the time of closest approach. Here you can basically see a two-dimensional mapping of the encounter, where we've basically got Apophis over here. It'll start, you know, some ways away from the Earth. It'll fly by. We'll see perigee, and then it'll fly up and out of the and away from the Earth. And we're going to track about 11 or 12 hours centered around the closest approach. As for the different packing structures that we try, it's a ton of them. So basically, in order of resolution and density, I suppose, we have at the top here hexagonal close packing in a very high density configuration. This is about 10,000 spheres, size something like 7 meters for this. So hexagonal close packing is the densest possible packing configuration for equal sized spheres, right? So this is when they were stacking cannonballs back in the medieval ages. This is the way they would do it so that nothing would fall down. You could get the most packed into one space, right? We also have what we call random polydisperse packing, again about 10,000 spheres, ranging from 2 meters to about 7 meters in radius. And here what we do is we generate a cloud of particles. We let them all collapse together gravitationally to create a sort of natural packing distribution. And then we carve away the outer layers to create the shape of Apophis and let that sort of settle under its own contact forces. We also have low resolution versions of both of those. And we have all different kinds of aggregates. Remember the different colors that I showed you a few slides before map to these same single uniform aggregate packing. That's what that UAP stands for. And we also have a mixed aggregate packing. And then for these ones that I've circled or square boxed in blue, we do different interior structures as well. And we have 9 of these where we try different size spherical cores or ellipsoidal cores. And I mentioned this might be a contact binary. It has this bilobate structure, so we test some like that as well, where we have a sort of ellipsoidal core and a spheroidal core, or 2 ellipsoids with their axes aligned or parallel, like that, just to try to see what different internal structures do to the deformation or the potential rotational changes. All right. Moving on to the actual results. I'm going to be showing you mostly results from the high-resolution random polydisperse packing cases here. This is the one that I think is probably the most interesting, or at least has the most clear results. So I said, rotational change is pretty likely, right? It's going to come in, it's going to get torqued by the Earth, and this should be relatively observable. And what we see here in this histogram is a likely change in period by as much as an increase of about 8 hours or a decrease of about 11. And very unlikely. There's only one case that we found in about 30 trials where the rotation state didn't really change much at all. So it's likely that the body that Apophis is going to spin up or spin down, but we don't know which one it's going to be because it depends on how it encounters the Earth, how it's facing as it encounters. You imagine, you know, if it's rotating into the Earth and the long axis points right towards it at the time of close approach, then it'll get this nice torque and spin up, or if it's just past that, then it might get spun down, torqued in the other direction. And so until we know the phase of Apophis as it comes close to the Earth, we're not going to know which of these situations we're in, but it's a pretty likely scenario that one of these will happen. And these provide good outer limits. This agrees with other studies that folks have done for the change in the rotational state. I said I would talk about the deformation, and here you're seeing that, and I want you to make a note of the y-axis scale here. This is microns. I told you Apophis is a 350-meter diameter body, about the size of the Eiffel Tower, right? So if the Eiffel Tower changed height by less than a millimeter, would anybody notice? Do you think we'd be able to observe that? If the Eiffel Tower is flying by the Earth at a tenth the distance to the moon, and suddenly it changes in length by about a meter, that's going to be incredibly difficult to see, even with a spacecraft there. So we're not expecting to see the deformation directly, right? This is really going to be more of a relaxation of the gravitational forces that are holding this rubble pile together, right? And it'll be mostly imperceptible. But it may lead to, well, the deformation actually changes as a result of the different packing structures that we have. So when we have this really dense packing, we actually get a much smaller strain along these axes than when we have this much looser random packing. And then these mixed packings with the irregular shape particles, which can increase the shear strength of the object while also increasing the porosity, right? So think about that. You have a more porous object, but because you have these irregular shapes, it actually holds together a little bit better than this random polydispersed case. So we can see basically with increasing porosity and decreasing shear strength, we get more strain. Great. But we don't actually know which of these is the most accurate model and how the cores match into this as well. So that's still a big question too. Seismicity. I don't know if there's going to be sound here, but if there is, you might want to turn it down just a little bit. So up on the top here, I've got this map for a single particle near the surface of Apophis. This is approximately what the seismic, 3 minutes, perfect. This is approximately what the, okay, cool. No sound is coming out, which is okay. But this is approximately what a single seismic source signal would look like here. We basically look at the velocity profile of the particles near and on the surface, and we pick out these large, short peaks, and we can plot those on this, on basically a power spectrum. So you take a Fourier transform into a seismologist, this will look very nice and pretty because this line says this is what the potential seismometer that will go on Ramses will measure. This is the theoretical self-noise of that seismometer, and this is the signal that a near surface this is a potential near-surface signal on Apophis. And so that says that this could be measurable by the seismometer that we're going to drop on there. So if Ramses is carrying a seismometer, which hopefully it does, and we can drop it on the surface, then it would likely measure some kind of short-period signals in and around the closest approach. And so when we're going to get these signals is over here. So time since simulation start, and I've matched perigee up here again as well at this sort of 4.5 hour mark after the simulation starts. And we can see this is a logarithmic histogram here, and so you'll see almost all of the short period seismic events occur at the end of the period of the significant tidal influence. That's when the tidal forces drop back down below the rotational forces in that diagram that I showed. There was that nice big curve at the start there. And they will mostly be shallow. Almost all of the seismic events happen in the top 30 meters in my simulation for this packing distribution at least. So they're going to be shallow, they'll occur after the tides have weakened, and they should be measurable by an in situ seismometer. That's great news, because seismic measurements are a great way to infer the interior structure, to get a measurement of the interior structure of a rubble pile asteroid, which is something we've never done before. And the only potential measurement we may have before that is from the Jura radar on the Hera mission. And hopefully we'll get radar measurements at Apophis as well. So these are my conclusions. Basically all the stuff that I've said before: irregular shapes, increased shear strength and porosity. Apophis will likely experience a change to its rotation, small and elastic tidal deformation, and it is likely to experience both long and short period seismic signals, with the short period signals happening just after perigee at shallow depths and should be measurable by an in situ seismometer. Thank you very much.
Thank you. Quick question.
You said, if I understand correctly, you said that size will be changing for 1 millimeter, right? What do you mean by change of size? Does it mean injecta of particles?
No.
Layer?
Essentially what you want to think about is this particle on the surface here.
Yeah.
Extends about 1 millimeter in that direction.
Okay, I see.
It's just a slight relaxation of the gravitational forces.
But if you consider that this is every particle in your simulation consists of a lot of dust particles. Will be they ejected or not?
No, there's not enough force. The tidal forcing doesn't go above the local gravitational forces, so we don't expect ejection of dust particles like that. No.
Okay, thanks.
Okay, I have a very quick one. You said that the spin changes cannot be known yet, but there will be, of course, more measurements when it comes again close. So will we know beforehand which way it should go?
Yeah, there's an apparition in 2028, I think, where we're going to get more data. That's pretty close to the close approach, right? And I know that the Czech group, Petr Pravic and his fellows are working hard on trying to constrain the spin change a little better. They don't want to commit to anything yet, but they've indicated that we might know a little bit more than we think we do about it at this stage, but nothing firm, and I don't think we'll get any strong statement about what the orientation at close approach will be until the 2028 apparition. There's a chance that Destiny Plus flies by Apophis. I don't know if that's been confirmed or not. So we might get actually some really good data from that, which could help out as well.
Okay, thank you. Next, we will have Rosemary Dorsey with the topic, the interstellar era of small body planetary science. So, please.
All right, slight change in topic to interstellar objects now. So, interstellar objects, or ISOs, are planetesimals that formed around other star systems that became unbound and orbit in the galaxy. And as such, they are really important messengers of carrying information about how planet formation works around other star systems. So this is a depiction of what happens when stars all around the galaxy eject planetesimals like we expect happened in our solar system in its early history. There are like three examples, three different star systems, and the coloured particles are the planetesimals ejected by that star. After some time orbiting in the galaxy, they spread out into streams of ISOs. But as you can see, after even a short amount of time, they are everywhere and they are mixed. So it's not very easy to trace these back, but the collective group tells us something about where they came from. So that's why ISOs are really important. We have three known ISOs. Hopefully you know about all of them. 1I Oumuamua was the first ISO that we found. It was an asteroid which confused everyone. Everyone was expecting these to be comets, and the first one that showed up had no coma, but it did have the orbit of a comet with non-gravitational forces, so that was confusing. It also was very small, similar to sort of like a large near-Earth object, and it was also tumbling with this large axis ratio, a really stretched or flattened shape that is extreme in the solar system. Not impossible, but not very well seen. The next one, 2I Borisov, was definitely a comet. Looked very similar to solar system comets in composition as well as behavior. And then lastly, just last year, the third interstellar object, 3I Atlas, was discovered. It's the largest of the three, the fastest. It's coming in at the fastest speed. A work that I'm on showed that it is probably the oldest planetesimal that we've ever observed, probably about twice as old as the solar system. So that's very cool. And it is very active, a very large coma and tail. So three very different objects that we've seen so far. And that's wonderful. The problem is that they were all discovered by different surveys. 1I and 3I from solar system surveys. 2I was found by an amateur astronomer looking very, very close to the sun, which other telescopes worth a lot of money weren't going to do. So the observational biases for finding each of these is very different. So trying to piece together an image based on the discovery of these three objects is very complicated and complex. So we need a sample of objects, ideally observed by the same survey, so we can understand what actually each of these objects is telling us. So that is where the Legacy Survey of Space and Time comes in, LSST, and hopefully you're familiar with this because it's going to start this year, very soon, hopefully, any day now. We've been saying for years. And so one of my recent works was to predict how many of these ISOs we're going to actually discover in the survey. So we use something called the Autotahi-Oxford model, which is a model of the population of ISOs in the local galaxy, the solar neighbourhood. And I won't go into too much details on this, but we predict between 6 and 51 ISOs will be discovered over the 10 years of this survey. Now, that range depends on the size distribution of ISOs based on 3 objects, 2 of which we can't see the size of directly. It's unknown what the size distribution of these objects is. So assuming some reasonable numbers, 6 to 51. And this number is for a single number density estimate, which is again also unknown to a few orders of magnitude. So this assumes the best estimates, but it could be different. Also with our ISOs, we see them coming in. They're first detected rather in LSST when they're coming in from the solar apex, the direction of the sun's motion through the galaxy. So they fly through the solar system. We see them on their way in. They're discovered almost anywhere on the sky within the survey footprint, which is quite interesting. And then they're last observed on their way out again. And so that range 6 to 51, it doesn't sound like that many compared to, the 3 that we have now. So I like to think positively about the pessimistic case. So bear with me. So 6 discoveries, what will that even tell us? So temporal information, we have 3 ISOs discovered in the last 8 years. We're going to find 6 in 10 years. That's quite an improvement, and it might tell us something about, are we seeing a background of objects coming in, or are we in a stream of objects? Are we in an ISO shower, to put it in sort of meteor terms? We might get a better constraint on the number density, how many of these things are out there. We're gonna see whether they're cometary or asteroidal. We only have 2 comets, 1 asteroid at the moment. Are they all comets and we just didn't see it with one eye? Is there anything that's definitely asteroidal? That will be interesting. And actually one of the results of my paper was that there will be some constraint on the size distribution slope. So our work showed that even with some number of ISOs that we discover is on the y-axis here, and the slope parameter, or the relative difference between the true slope and what you can best estimate the slope with, is on the x-axis, and for about 5 or 6 ISOs, you can constrain the slope to about, or within like 1.5. Now, the value is, I think one of the estimates at the moment is Q of 3, so that's from 1.5 to 4.5, which is a bit of a range, but even 6 objects tells us some information. And then if you remember what the other end of the range was, that was 51 ISOs. That's this blue dashed line, and that's 0.5. So that's a dramatic improvement on how we're going to constrain things. So it'll tell us something, is the optimistic end of that. The other thing we've seen with our 3 ISOs that we know is, particularly with 3i Atlas, the opportunities to observe these, not just from the Earth. So the really cool thing was that we had a lot of warning with 3i, and it's going to stick around a long time, hopefully. And so we were able to, or the community was able to plan to observe 3i with lots of different instruments. So here is a plan, I think produced a while ago last year, by ESA, of the different spacecraft that could possibly, and we're planning to observe 3i. I'm not up to date on whether any of these happened or how successful they were, but it's 3 different, so there's ESA's Mars Express, the ExoMars Trace Gas Orbiter, and then also the JUICE mission on its way to Jupiter. observing 3I at different places. And to include the other main player, NASA's missions, and these are the circled ones. I've taken this from a presentation at the Small Bodies Assessment Group earlier this month. And there's about 10 spacecraft here that attempted or successfully made observations of 3I. So that's really cool that we can do this. And my favorite one, this GIF, I'm not expecting you to see this, but you should go check this out on your own. Somewhere in this crosshair is a very, very faint detection of 3I from the Perseverance rover on Mars, which is, as well as singing itself happy birthday every year, got to see a comet. So I thought that was quite cool. Other missions to ISOs, so you'll hear about Comet Interceptor later, but if you don't know about it, it's a flyby mission of a dynamically new comet that's going to launch in 2029. It's supposed to go to a comet from our solar system, but everyone thinks it'd be cool if it went to a comet from a different solar system. 3I didn't quite make the cut, even though Comet Interceptor hasn't launched yet, it didn't quite get close enough. And so there are some challenges with visiting an ISO with something like Comet Interceptor. The first one is that ISOs are fast, right? They're unbound from our solar system, so they're moving faster than any other comet that we're going to try and visit. That makes taking really nice, clear images a little bit harder. And Comet Interceptor is designed to be fast anyway, it adds more problems. Their orbits are inclined, they're coming in from anywhere in the galaxy, so they're not in the plane of our solar system. And we don't want to go out of the plane because that takes a lot of energy. So there's really few orbits that are gonna line up just right for visiting them. And the perihelia may be very distant. I mean, the 3 ISOs that we have had perihelion within about 2 AU. Most of the ISOs that come through the solar system are further away than that. So traveling to get there is another constraint. So really a successful mission to an interstellar object is going to look like a large delta V budget, a little bit larger than Comet Interceptor, probably a lot larger than Comet Interceptor, and something that's parked and ready, which I think the community is sort of in agreement of, that these ISOs are going to come in when we don't expect them, just like 3I, and we need something that's prepared for their short visit. Thank you. So my novel idea that I just want to throw out, lots of parked and ready spacecraft sit in the L2. This is where Comet Interceptor is going to sit and wait for its target. It hasn't picked one yet, but it will sit there and wait until a target arrives before flying off. This is also, I think, where the James Webb Space Telescope sits, and it's everyone likes parking stuff there so that it's ready to go. But I think we're thinking a little bit too close to home for these ISOs that don't quite get close enough to us. And why not somewhere else out a bit further? Somewhere like Mars. We've seen lots of the Mars spacecraft contributing to the 3I observations. And the JUICE mission, which is on its way to Jupiter. And these would be also great for discovering these ISOs in the first place with a distant observatory, finding these things on the way in, giving us some warning, giving us some more time and preparation. So I think this is sort of where things are going to head in the future. We're going to have some different ideas and really push the boundaries of trying to find these objects, because they are going to tell us a lot about the galaxy, hopefully. So this is just my summary, and if you take away anything from this talk, I hope it's that interstellar objects are going to be the next thing that tell us something about planet formation, and with LSST it's going to be very, very exciting, even with 6 ISOs, which is pessimistic but still positive. My opinion, I suppose, is that ISO missions will need a lot of careful consideration and then a couple of new innovative ideas to really boost the scientific return. And that's all I have for you. Thank you very much.
Yeah. Thank you, Rosemary. Question? Or go with Michael.
Very nice overview. About the detection, I'm sometimes wondering, maybe, do you think we are missing interstellar objects in the surveys because the discovery pipelines are somewhat tuned to asteroids, specifically near-Earth asteroids?
So that's an interesting question. ISOs are kind of just extra fast NEOs. So I think NEO surveys, near-Earth object surveys, are the best ones to detect them. A specific problem with LSST is that it's a southern hemisphere survey. If I showed you that graph here, this is the LSST footprint. ISOs come in from the north, where we're not pointing at all with LSST. And so we actually pick them up when they're on their way through, and you can sort of see they go from here to here. So their first detection is when they finally land in the footprint. So, pardon? The footprint has changed? Is it? No, they're not going to look at the solar apex. No, yes, so we're going to get them when they're further and closer in. So if we had a northern-based telescope like LSST but in the north, that would actually be very, very helpful, and there have been suggestions of that. So fingers crossed, something in Europe maybe.
Sure, very, very rapidly. A quick one.
Yeah. On one slide, you were showing how a successful mission look like. Yeah, could you show this? So you said that the orbits are inclined.
Yes,
Yeah.
interstellar objects.
We have three objects known to one. And one of them is almost in the...
Yes.
In my understanding, this data, it is a very limited set of data indeed. But it suggests it is not. It is matter to study, but it looks like that the orbit are not inclined.
Right, yeah. So 3i is a special case. So the Ōtautahi Oxford model has a distribution of inclinations for these objects, and it's not impossible to have an ecliptic orbit, but it's unlikely. It's not the preferential direction. Yes. So yes. Yes, so most likely the interstellar objects that we will see will not be in the ecliptic, but so the opportunities to visit them will be when they go through their ascending node or descending node. That'll be the opportunities.
Thank you, Rosemary. We will continue now with 3i and with Zurich Ray with the topic extreme negative polarization of new interstellar comet 3i Atlas. Please.
Thank you. Yes, so I am a postdoctoral researcher at the University of Helsinki, and my specialty is in polarimetric observations of solar system objects, and more recently, interstellar objects. So today I'll be speaking about our polarimetric study of 3i Atlas, done by myself and the team shown here, which include many people in the room and also the previous speakers. So Rosemary gave a very nice introduction to ISOs. So 3i Atlas was discovered in July of last year, and it was inbound towards the inner solar system at a large heliocentric distance of around 4.5. So this gave astronomers around the world a brilliant opportunity to observe and monitor this object as it came in towards the sun, including ourselves, who jumped on this opportunity and immediately submitted telescope proposals to take polarimetric observations. So for context, 1i Oumuamua was discovered on its way out from the solar system, and it was at a faint magnitude, too faint for polarimetric observations to be taken even from the largest facilities. And 2i Borisov was discovered pre-perihelion, but polarimetric observations didn't begin until post-perihelion. So I'll be discussing these a little bit as well to compare to 3i Atlas. So our polarimetric observations, we used 3 facilities around the world. We used the 8.2 VLT in Paranal in Chile. We used the 2.5 Nordic Optical Telescope, which is based in La Palma in Spain. And then the 2-meter RCC telescope at the Rosen Observatory in Bulgaria. So a little bit of introduction to polarimetry of solar system objects. So light from natural sources like the sun is generally unpolarized and then becomes partially linearly polarized once it's scattered by a solid surface of an object, or in this case, the cometary dust particles in the coma and the tail. And we tend to measure this polarization as a function of phase angle, this angle here. And once we have enough measurements, we can plot the so-called polarimetric phase curve. And it's found for all solar system objects. The polarimetric phase curve generally has this shape, which has negative polarization at small phase angles and a positive polarization at larger phase angles. The angle at which it switches sign is known as the inversion angle, and the other important parameters in this curve are the values of the values of minimum and maximum polarization and the phase angle they occur at, and the slope of the curve here at inversion angle. So even though all solar system objects show this general trend, the overall shape of this curve, and therefore these important parameters, depend on the properties of the scattering medium. So in this case, for comets, this depends on the size of the dust particles, the size distribution, their composition, their structure, their porosity, and so on. And so for comets, the properties of the dust can vary depending on its orbit. So the heliocentric distance governs the temperature of the nucleus, which in turn governs the gas emission, which in turn governs the dust and gas properties. But despite this, we can see trends in comets from our solar system. So in general, comets are found to fit into one of two categories: either high polarization comets, which show maximum around 25 to 30, or low polarization comets, which show a maximum of 5 to 15. There's a few different explanations offered to explain this difference. On the one hand, it's the dust to gas ratio. The higher the dust, the more gas, the less dust there is, the more diluted the polarization signal is, we get lower polarization. And the higher the dust to gas ratio, the higher the polarization. And then another explanation is due to simply the intrinsic properties of the dust particles themselves. Now, it's found that most comets can fit into one of two of these categories, but there's a few exceptional cases. The most well-known case is that of comet Hale-Bopp, which is shown by this curve number 3 here, or this green curve here, shown at these smaller phase angles. Now, Hale-Bopp at certain phase angles has been found to have around 4% higher polarization than even high Pmax comets. And for the longest time, Hale-Bopp remained the only comet to have this particularly higher polarization. And this led to the definition of a unique Hale-Bopp-like comet in polarimetry. This was the case until 2I Borisov came along. So 2I Borisov, it was observed post-perihelion in 2019, in 2020. Its measurements are shown here in the blue, and as you can see, its polarization properties aligned very nicely to that of Hale-Bopp. And so 2I Borisov was the first interstellar object observed polarimetrically, and it fit into this unique Hale-Bopp-like category. And the way that these stranger polarization properties are explained are due to these smaller particles in the coma. And so, of course, 3I Atlas came along, and so we were curious into which of these categories could 3I Atlas fit. And so we took polarimetric observations pre-perihelion and also post-perihelion, which I'll be presenting for the first time publicly today. And here I show in the black the pre-perihelion polarimetric observations of 3I Atlas. As you can see, we see the expected negative and positive polarization, but it shows a much deeper and more narrow negative polarization branch compared to, well, anything we've really seen before. In particular, it has a very small minimum of around minus 2.7. This is almost unheard of for comets. And so also it was characterized by a very small inversion angle around 17, which is much smaller than the typical 20 to 22 found for other typical comets. So 3i Atlas was the second interstellar object observed polarimetrically, and it looks like it doesn't fit into anything we've really seen before, and so this could be a unique or new class of polarimetric comet. So to explain these unusual polarimetric signature, we look to theoretical studies. In particular, light scattering simulations and experimental studies find that in order to replicate this deep and narrow negative branch, you must include some bright scatterers in the particles. And in here, this is a study done by Ivanov et al. They did light scattering simulations, and they found that to replicate this deep negative branch, in addition to silicate and organic materials, they had to include a water ice or CO2 ice element inside their particles. And they found that the size of the particles and the porosity had an effect on the depth of this negative branch and its position. And so from this, we have what we've published, our first paper, which you can, there's a link here if you're interested. And the main conclusions from this paper are that 3i Atlas is characterized by extremely deep and narrow negative branch. It represents possibly a new and unique polarimetric class, and that its coma could be dominated by large porous particles consisting of a mix of bright and dark scatterers. As I mentioned, those were the pre-perihelion observations already published, and ever since perihelion, we've been taking new post-polarimetric observations. Perihelion happened on the 30th of October, but at this time we could not observe the comet due to solar conjunction. So the comet re-emerged from behind the sun in early November, and we've been taking observations ever since, again using these same three facilities. However, 2 independent studies have already beat us to it and have published their results. So I'll be speaking about all 3 of them to have a bit of a comparison. So again, these are just the pre-perihelion observations. I've removed all the other objects just to make things a bit clearer. The first study to publish their results was that by Zheldobruyukov et al. Hope I've pronounced that okay. Their observations started around 2 weeks after perihelion, and their observations went on for about 2 weeks. And as you can see, they measured polarization properties slightly lower, slightly different compared to these pre-perihelion observations. And so to explain this, they also used light scattering simulations. And so to explain the pre-perihelion observations with the deep and narrow negative branch, they found that they also had to include a water component as the bright scatterer in order to replicate this deep negative branch, in addition to silicate and organic materials. And then to explain the post-perihelion observations, they found that they simply had to remove this ice-water component as the bright scatterer. And so they explained this change in polarization as being due to this water-ice component surviving inside the particles pre-perihelion beyond the snow line, and then the post-perihelion observations, basically these water-ice particles were not surviving, were sublimating, disappearing within the snow line. So this is how they explained this difference. And then just last week, there was a new independent study released by Choi et al. And their observations started at a very similar time as this previous study, just a couple of days later. And this time, they found that the post-perihelion observations actually aligned very closely to the pre-perihelion observations. And so this was despite, so they found that the polarization was stable both pre and post-perihelion and before and beyond the snow line. And so they, okay, thanks. And so they explained this stability in polarization as so this unique polarization signature would be due to the intrinsic properties of the dust particles rather than the disappearance or the inclusion of a volatile component. And here are our measurements shown in the red. And as you can see, our measurements actually also align very closely with these pre-perihelion observations. And so our measurements also support more so the hypothesis that this strange polarization signature is due to the intrinsic properties of the particles rather than a volatile element. And our measurements also covered both the before and beyond the snow line. And another interesting thing from these new measurements is that pre-perihelion, our observation stopped at around a phase angle 7, but these newer measurements, we've been able to sample all the way to phase angle 1. And with these new measurements, actually our minimum value of polarization has been redefined to about -3, so even more extreme than we previously thought. And so here I leave you with the conclusion slide. These are the things that I already mentioned before, except so 3 Atlas is characterized by an extremely deep and narrow negative branch, but according to our measurements, this remains stable despite the perihelion and the snowline passage, and that this unique polarization signature could be due to simply the intrinsic properties of the dust particles. And thank you very much for listening.
Okay, thank you. Very interesting and fresh results. Questions? Evgeny?
I just would like to say that this finding for modeling, I mean blue line, yes, this blue line, it suggests up to 40% of water ice particles on the scale of micron sized. There is a near-infrared spectroscopy result already published 2025. Karen Misch is second author. I don't remember first one, sorry. Who get exactly the same volume concentration of water ice particles. This is one point. Second point, we published, I mean, Zheltobryukov et al. I am second author there. It has been published only first section of the measurements. The difference with it disappears in our earliest December measurement. It was, if I recall correctly, December 12th. Unfortunately, between 26th of November and 12th of December, we didn't have good weather. So
Was this over the change of the snow line, or how do
yeah,
you explain this?
it is now under consideration, our article, where we actually compute snow line. You will be shocked with its location.
Yeah, I noticed a changing value in your papers of the snow line.
Yeah, so it's kind of, we gave some example of, what was, Marta Hanner, 1981. So she found that water ice particles, if you consider snow line not like immediate disappearance, but time of life of water ice particles, it is 158 years for micron-sized particles at a distance 2.3 astronomical unit. So it's much closer than you think.
Okay, good. Other comments, questions? Well, excellent. Let's thank all the speakers for this morning session. And you can convene after the coffee break again.
beep, beep. Okay, this is room audio, it sounds alright. So now we have room audio, this sounds good. Olas, come in, can you please check Takka audio? Does this room mic sound good? Does it need more or less audio? Speaking. Can you please check Takka audio? I want to see if the room mic is good level. Speaking. I am speaking. Station. Status update, please. Can you repeat that? I barely heard you. Hold again when you're listening. Coca-Cola. Does the audio sound good, Olas? Speaking and speaking. Yes? Levels need adjusting as well? Or maybe just this one input. Will do.
take it one.
Just gonna go front of the room again and then speak again. I'm speaking. This is not fine.
from below, so everyone sees the sidewalks. Exactly.
Okay, good morning, everybody. I hope now that we're on the third day, everyone's a bit slightly hungover, maybe, from the conference and all the talks we've heard today at this session for solar system missions, small body missions, rather. We're going to have 3 talks. First is from Tarvi Tapandi Kupkulgur. Ignore me wearing the Kupkulgur shirt. I am very unbiased right now. I wanted to quickly ask, does anyone know Jonathan Klesner? Or you're here. Okay, great. And does anyone know Sabrina Suki, who's supposed to be the second presenter? Good. But yeah, thank you for coming here. It's lovely to see a full room because in my experience, as conferences go longer, the rooms get shallower and shallower. So it's good to see a lot of good, happy, energetic faces. Our first presentation is going to be from Tarvi Tapandi, who's going to talk about the Kupkulgur project and the current status update of that. So with that, Tarvi, I will let you have your way with the audience.
Yes, thank you. So, good morning, people. Kupkulgur, hopefully you've seen it driving around on the ground floor. For those who haven't spoken to us, I'll start with a brief introduction on what is Kupkulgur, and then I'll move on to the this year's status update. So, Kupkulgur, it is a small modular platform for lunar missions. I call it a platform because, as you can see from this model, what we're making is the platform underneath, i.e. the aluminum bits and the part beneath, and the box on top would be left for a payload that if anyone wanted, they could develop and then send to the moon. Currently, we're developing it purely for the autonomy side of things because we've yet to find a partner who would actually go with us to the moon. But the idea behind this is that when someone wants to send their payload to the moon, currently they will have to either build a rover from scratch or develop a tightly integrated solution into someone else's rover. But what we're aiming for is the modularity that Cube satellites have provided, so we're a Cube rover. And how we got to Kupkulgur was that from Tartu Observatory we already had experience in various fields, simulation, we had built satellites, we knew about autonomy based on visual methods, and had built robotics. There was nothing really stopping technologically from us developing something like this. And we saw that there was interest in this, so let's go to the moon. I also called it a testing platform. That's because even if right now we're not actively developing for the moon, what we're actively developing for is to allow testing of various payloads on top of the Kupkulgur platform. The best example of this is that right now we can mount a cheese plate depicted here beneath. And even though the current payload depicted in the image is nowhere standardized, we already can gather data with our rover. Accessible to our partners who use Kupkulgur are various sensors, including wheel encoders, an inertial measurement unit, and our camera. And our electrical power system is developed purely to provide various voltage outputs such that we can be adaptable to various payloads. When gathering data, we tend to do it in the Lunar Analog Facility, henceforth to be referred to as the bunker, at the Tartu Observatory. As you can see, a visually striking image could fool someone that it's actually the moon. More recently, though, we developed what we call the sun, which is basically a kilowatt of LEDs, and the room isn't so pitch black anymore. But this powerful light, it does help development. And purely our project has already worked with various companies, in this case Estonian ones, and I would like to especially bring out that our rover's data gathered in the bunker is used for one of our partners, ProExpert RPA. In terms of current developments, there are three main avenues that we're going towards. One is just general platform updates, another is development of autonomy, and we're also developing a camera of our own. All of this we do at Tartu Observatory. Currently our projects are funded by ACE, which is the Estonian government. Mentioned the camera. The camera is that we saw that there was no good camera for us in terms of the space-grade cameras. They're all for orbital operations and not really for planetary autonomy. And we have some restrictions for our platform. For example, since we want to also explore the darker areas of the moon, we want it to be really capable in low light conditions, i.e. Big pixels to gather as much light as possible. We also want to be capable of neural network acceleration. This means that we would have an FPGA on board that could work with the raw data directly. The camera, as I mentioned, is one of the two major ongoing projects. The other is autonomy, which I'll get to later on. And so far, we've evaluated various sensors, and we made our initial selection, and evaluation and work on one of them will continue. In terms of the platform upgrades, a whole bunch of the electronics have been upgraded. Starting with the electrical power system. This is this part right here. Its battery capacity has doubled since last year. There was a presentation here where we depicted it, but now it's actually integrated and driving around on the rover. We're also developing a flight computer. This can be taken in two steps. First, we're developing a carrier board for an NVIDIA Jetson module and a peripheral board to go alongside it. This would then be the compute platform on board that would be capable of actually doing autonomy. And for the truly vital stuff, for our rover to move around, perhaps as a remote-controlled car, essentially, we want something that's also capable of fault detection, isolation, and recovery, and is space-ready. And that would be one of the boards in here. And we're also developing a communication module, but it's in the very preliminary stages. In terms of the mechanics, I won't go into it too much, because the wheel design part, it'll be covered later on today in this very same room by my colleague Silver. But other than that, we're also looking into other platform configurations, but we're sticking with our 2-unit one for now, because a smaller rover is more difficult to work with, and if we go bigger, we can just increase battery capacity, but autonomy will still work. And we're also preparing for a switch to brushless DC motors, so the entire hardware side in terms of that, but also the electronics need to be redesigned. Rover software, as I mentioned, the other major project. What we want to do is utilize ROS2, NAV2 for it, though not in its very pure basic way, but we want to adapt it, optimize it, but also start utilizing a map that has height information, because we're not moving around in a warehouse like it might be used for so far, but we do want to detect obstacles and do path planning accordingly. We also have an unscented Kalman filter for onboard autonomy. This here is the ground truth trajectory, for example, that was gathered in the bunker. And of course, everything we want to do is camera-based. Localization has been some other sensors adapted to it, but we're truly focusing on cameras. And my personal project has been making the onboard software, the higher level robotics software, be developed in Docker containers, because as a student project, we have plenty of students coming in and out, and if 2 students want to work on the same rover on the same day, we can't just have one leave the rover with the modifications they made. It's made it really convenient. A part of the autonomy is also doing some machine learning research, namely for obstacle detection. We are able to predict depth. From an input image, we predict depth. And to train it to be even better, if nothing else, we can also have a mock payload of a LiDAR, which is sparse depth. We combine it with the camera data and get dense depth image. And in terms of machine learning, because we're talking about space, the most important parts are that we optimize it for low power devices, but also this comes out in the way that some models, some of the more cooler models from recent times, are based on transformers, but they're not really that optimizable. So this is also an avenue of research for us. The other side of software is the mission control interface. And over the last year, we've added multi-rover support. We can now control multiple rovers from the same interface. Also, usability and responsiveness have been validated. The user experience has been enhanced, and security changes have been made to allow for less risk. And of course, we're also continuing it with, alongside other rover developments, platform upgrades, and integrating the autonomy input methods such as mission planning tools, and we're also improving reliability and low latency data handling. This is what we've been doing with the platform so far. I would also like to point out that so far, not just within the previous year, we have 11 theses successfully defended in both master's and bachelor level. 9 are currently in progress, and we've got some recognition from our work as well. For example, my colleague Silver was giving a TEDx talk in Tallinn a couple of months ago, and to me the most important one for us is that students now find us from all around the world, that we are truly making a name for ourselves. This next year we have a whole bunch of goals. We'll see exactly how far we go, but of course we want to continue and finish our projects, continue working with our partners, find more, if not find more of them, and of course continue our research. We want to integrate our rover even better. We also want to simplify the process of manufacturing our rovers, and even though it would now then be simplified, we're also looking into simulations. And lastly, because so far we've been using our bunker, there's no real reason not to gather data. There's more to be learned out there, for example, gathering data in a quarry. All of this has been made possible by this wonderful team of people. I'm very proud. Though I do admit that some people are missing in many of those newer ones who I haven't got pictures for yet. And of course, if you have any more questions, come see the rover driving around, come talk to us. We are on the ground floor. Yes, thank you.
Thank you, Tarvi. Any quick questions? Yes, Henrik.
Okay, thank you, Tarvi. Henrik Kahnpää from University of Tartu. Yes, so have you considered using a stereo camera? Because then you would be for detection of in-depth detection.
Yes, we have. Our current methods for depth prediction, they're based on a single camera, but as can be seen, luckily this is a hollow model, we're looking into stereo cameras, yes. So to answer your quickly, yes, we are looking into stereo cameras.
I will ask a follow-up question then to Henrik. What challenges are there with a stereo system compared to a monocular system that we currently use? Why not go stereo straight away?
Frankly, a single camera is simpler. It's not that there is less data to be lost in the process of it in terms of dual cameras, but for a singular one it's simpler and we can just pipe it into our depth pipeline. For stereo we will need to do actual algorithmic approach of finding the points, matching them with the other camera. There's also temporal delays between the camera. They would need to have the exact, what's the word I'm looking for, capture the frame at the exact same time. So those are the main challenges in terms of that.
Good answer. Any other questions? Yes.
you're going to use this 18650 batteries. So do you mean, do you expect no charging during?
We do expect charging during an actual mission. It's just that we haven't started with the solar cells yet.
Okay. And did you make some any assessment how long it will keep charge at minus 170 degrees Celsius?
We're not counting for those low temperatures.
So you're not going to survive one night?
As with basically any mission so far, no.
Okay.
Any other quick questions? This is only a session for 3 talks, so we can have more questions and have a discussion. Yes?
Yeah, well, I can shout it, so no need to.
Thank you.
I was wondering about the lunar testing facility that you have. Do you have a vacuum chamber? Because the metals of moving parts, they're going to be affected by like fusing together. And also the dust environment is going to be crap on the moon. So have you like done any specific tests on those?
In terms of dust, it's something that we're actively looking into. Of course, none of this is really within the lunar analog facility, because that's purely to mimic the visual side of things and get the rover driving around. In terms of the vacuum chamber, the Tartu Observatory has, what's a good word for it, quite extensive testing facilities, including a vacuum chamber. But we haven't gotten to that stage yet.
Any other questions? Yes.
You were comparing it to the convenience of CubeSats, but I was wondering if there's like delivery systems to the moon, like landing systems that are like, I don't know, standardized for that size as well, or if that's like on the customer.
Hopefully soon. As far as I know, there's no standard in terms of the landing system yet. But of course, it's just waiting for a standard to be established then. But we're not developing the lander side of things.
I would like to add to Tarvi's answer on that, because I can. We are actually in conversation with several companies who are trying to be standardized landers to the moon in the future. And we're actually giving them feedback as end user customers, as in who they would carry to the moon. And we're giving them feedback into what kind of communication requirements we have. If the lander can even charge the rover, that takes a lot of load from the rover of like solar charging itself. So it is hopefully in the future, but as of today, they're a work in progress, and all we can do is prepare ourselves as best as we can. So we stay in touch, basically. Okay, any more questions? If not, I would implore everyone to applaud Tarvi once again for his stellar presentation. And we'd invite the next presenter, Jonathan. Oh, Henrik, you have one more question.
No. Just a comment that we have plenty of empty seats, so don't be shy.
Yes, come sit down, enjoy the presentation from Jonathan next. I will ask again, does anyone in the room know Sabrina Suki, who was supposed to present over Zoom? Our next speaker is going to be Jonathan Klesse. Yes. He's going to discuss the Apophis interceptor mission, which sounds extremely exciting. So Jonathan, take it away.
Yeah, welcome everyone. Thank you for attending my talk today. Since we had an Apophis class before in the session, I will briefly skip the introduction of the asteroid itself, except for the fact that it will miss Earth during its close encounter in 2029. And maybe I get a pointer to continue with the presentation. Otherwise, you might do it from your laptop and like. Okay. Perfect. So, going straight to the mission itself, the Apophis Interceptor mission aims to demonstrate the technologies required for flyby-type investigations of near-Earth asteroids based on small satellites doing the Earth-closest approach of Apophis in 2029. That's quite a big topic for a CubeSat mission we aim to do. So we want to use 2 16-unit CubeSats to perform this task, have some redundancy on system level. And on these satellites, we want to implement several payloads. First of all, we have an imager to capture the visual details of Apophis during the approach. And secondly, we have magnetometers installed on board to perform secondary experiments over the course of the entire mission, monitoring the Van Allen belts and the magnetic fields. Furthermore, we consider additional smaller payloads for further experiments and further technology development. Since our key mission objectives are not only to have the scientific part with characterization of Apophis details and the magnetic field measurements, but also basically verifying that we have a CubeSat that is capable for future deep space missions. So, how do we actually get there? We aim to have a GTO rideshare mission that gets us to a trajectory rather close, and then we raise our apogee to reach our final orbit. After doing so, we are waiting till the asteroid arrives, and then we start imaging and observing the asteroid from both sides while it flies through our satellite constellation. So this seems to be rather simple, but in practice, the orbit trajectory is much more complex. First of all, having or being part of a rideshare means that we are not the first contractor, so we don't have the priority in selecting when to start and to which location we start. However, we figured out that when a satellite is sent to a geostationary orbit, there is at least one launch window a day where we could align our target trajectory with the geosatellite, since we basically only care about the Earth-centered inertial frame and not the geoslot. And after being in this GTO orbit, we need to raise our perigee further and to avoid bleeding out apogee height over the mission. And doing this maneuver, we also increase our inclination to avoid interferences with other geosatellites, since we will cross the geostationary ring with each orbit. Then, next, after doing this, we will raise the apogee to our target height. However, since we only have CubeSat thrusters, we have to do this in at least 5 steps, 5 orbits to get the impulse done. An additional issue we have is that since we are a CubeSat, we don't have sufficient propellant to counteract orbital drifts that will occur during the mission. You can see this in this image here in the gray sections. So you can observe that the orbit will drift over time, and we have no way of counteracting that. So we have to account for that when designing the initial trajectory. And the last point that's really important is, since we want to observe Apophis from close by, we have to synchronize this orbit trajectory with our actual satellite location. So to do this, we have a waiting orbit somewhere in the middle. You can see it here, like this line, for example. There we will wait for quite some time to get our orbital drift synchronized with our true anomaly, since the orbital drift and true anomaly variations, or orbital period variations, scale differently depending on orbit height. So there's some leeway we have to find perfect trajectory. Then, after the maneuver, for decommissioning, I see there are some words missing there in the presentation. We want to lower the perigee below 30 kilometers in the end to make sure the satellite will burn up and doesn't endanger any things in orbit, preventing space debris. So, now getting to the flyby experiment. In the video on the left, you can see like a 4 times sped up version of the most important 2 minutes of this flyby. It's only captured at 0.5 FPS with like 1% of the actual image quality we would expect on our imager, just to save computational efforts during the simulation. The actual high precision time we have for the observations are only like, are only approximately 30 seconds, where we have a ground sampling distance above 10 meters, or a ground resolution actually. But during this time, we want to basically cover everything you can do with a camera, so get all the position, trajectory, size, and dimension of the asteroid more confined, and basically support the other missions like Ramses or Osiris Apex and that. Next up, you have another nice simulation, this time from an asteroid-centered view, showing where the satellites fly through and with the coverage and the ground track of the satellites during the flyby. So you can observe that there's basically a full coverage using 2 satellites. In practice, the quality of the images might vary, since only one side of the asteroid is actually sunlit, and only this section is actually really well observable. The dark side needs really long exposure times, and this really depends how well we are actually able to track the satellite to avoid drift, so we don't have blurry images in the end. On the other side, the nominal orbital observation distance is set to 30 kilometers, so we have like a safe distance, avoiding collisions with Ramses, which is flying with the asteroid, and also avoiding the collision with the asteroid itself. And as you can see, we have really high angular rates when trying to track the asteroid with our camera, which is unusual for CubeSats. Like, there is basically no system available that could accomplish this requirement of these more than 15 degrees per second angular rate. So this is something we have to implement ourselves. So next up, our primary payload, the imager. Just a quick overview. We want to accomplish like a 1 meter ground sampling distance during our closest distance. And for that, we basically take an imager with a focal length as long as possible as it fits inside the satellite. You will see an image of that later. And the sensor is based on a 3D Plus version, a space-rated camera sensor, basically. And as I told you before, the sunlit side is really well observable. We actually don't even need to track the asteroid to get nice images due to the expected exposure time being only 0.05 milliseconds. Then, let's get to the second experiment, which is the magnetic field monitoring. As you can see here, our interceptor mission orbit basically covers all the relevant magnetic spheres, plasmasphere, the radiation belt of Earth. So there is a great opportunity to further characterize these regions with additional experiments and basically cover gaps from previous missions. Because I think the last missions that did these kinds of measurements kind of ended in 2024, if I'm not mistaken. So continuing this research is a rather relevant task. So The magnetic field is expected to vary vastly across our orbit as well, since we will be at quite a distance. So the instrument itself has to have a range from 5 nanoteslas to 40 kilo nanoteslas. Well, the sensor itself will be provided by a different university in Germany, the TU Braunschweig. And we have another compact digital spectrometer as an opportunity payload to measure the energy spectrum to better correlate the things. So in summary, we have the flyby experiment with the imager, the magnetic field monitoring, and then we consider further additional experiments. For example, some VLEO experiments that utilize us having such a high apogee so that at mission end we can basically lower our perigee first a little bit to get into the VLEO region and then just stay there for several orbits, bleeding some apogee, we don't care at this point, and get some nice information about drag stuff. So that could be useful for further application in the future. An additional thing is having some other technology experiments, some SSA observations maybe, something we will come up with in the next months. So, giving you an overview of our timeline. The phase 0 with the project Neolight is completed. We are currently close to finishing our phase A analysis. The evaluation at DLR in Germany is happening next month, so I'm looking forward to it. In case we achieve the funding, which is still a bit unknown, would be that we would continue with PDR on the second phase of 2026 and then go to CDR in 2027. So it's a really tight schedule for a rather complex mission, but we still think that this is kind of feasible to accomplish. Then the phase in orbit. The most relevant part here is like the commissioning phase. We need to get our propulsion and IOCS system online as soon as possible, since we need to start with our orbit maneuvers so that we can actually have these waiting orbits to synchronize our trajectory with the target. So, last but not least, a quick overview of our space segment, the satellite itself. You can see here we have like an 8-unit propulsion module, which supplies the 250 delta V, meters per second delta V. We will have like a 5mm radiation shield on the upper half of the satellite to protect all the electronics, to get down to a level of still 30 kilohertz. So the instruments themselves still need additional spot shielding if necessary. Then to get down with the payload data that we want to downlink, like we will get approximately 75 gigabytes of scientific data in the form of camera images, and we want to get them down at some point. So we need, or we want some S and X-band transceivers to accomplish that, getting like, I think, almost 20 megabytes per day down. To prioritize images, to get like the best ones first, we aim to implement some AI decision-making procedures on board as well. So we have a Jetson module implemented as well, which also does some image pre-processing for certain tasks. For example, since there is no star tracker able to accommodate our high slew rates, we want to implement some optical tracking, and for that we need some image pipeline, and this is managed by the Jetson as well, converting the image to some quaternions that can then be forwarded to the AOCS system. So far we already implemented a preliminary version, and soon we will test this on our currently flying satellite in orbit. It's a 6-unit CubeSat, and it already has a Jetson, and it's nice to implement things in orbit even if we don't have this satellite here yet. Another thing that's really noteworthy is our rather large battery pack here. This is needed to maintain fully operational during the eclipse season in March, which leads to some, like, at the maximum 2.5 hours of eclipse time. And we don't want to freeze there. Yeah. Overall, we think the mission is feasible, since there's basically a solution for every issue we came up with so far. So the main consideration is now getting the stuff implemented and acquire the funding for it. Like, in the end, Apophis is a really rare opportunity to investigate asteroids that close to Earth, and usually you don't have the opportunity to be this cheap and do it with CubeSats. And last but not least, we are still in the process of acquiring funding, since even though it is a magnitude cheaper than previous asteroid missions, it is still a rather complex task and challenging to get the funding for it as a university. Still, the development could be utilized for future extraterrestrial missions, science and planetary defense applications alike. So if we are able to track the asteroid, we are able to track anything else, basically. So we can use it for observation of other satellites, space debris, and other objects in space. Thank you for your attention.
Thank you, Jonathan. We have a lot of time to take some questions and have a good discussion. So many hands. I'll go from the front row.
Thank you. Very nice presentation. I have some suggestion how you can greatly enhance scientific return. Because you have two spacecrafts flying by. So there is technique referred in the literature as a phase ratio. So when you take the same area at different phase angles and then take ratio. And that could, if you properly choose phase angles at which you will do, you can investigate microphysics of dust on top and measure relief on top, like separately these effects.
Yeah.
I think to enhance, you need to think out how to organize rendezvous with asteroid at necessary phase angles for that.
Yeah.
So then just using images, you can get much more information than just analyzing pictures.
Yeah. However, we are unfortunately not able to do a rendezvous itself. This is like limited to the Ramses and Osiris apex.
I understand, yeah, but you need to figure out what is the angle. We can discuss later.
Yeah, of course.
Thank you for the great presentation. I was wondering, is there any idea already how to achieve this high slew rate and even more the high slew acceleration for such a relatively big CubeSat?
Yeah, exactly. So here you can see like really large reaction wheels compared to the satellite size. And you can also see that it deviates from the usual either 90-degree configuration and the normal pyramid configuration that has a much more steeper angle. And having them only like tilted 30 degrees towards the backplane here, we are achieving a much higher slew torque in direction orthogonal to the solar panels. So when we actually try to rotate the spacecraft in one certain direction, we get a much, much higher slew rate than necessary. So at the moment, if this configuration would fly and would work perfectly, we were able to slew the spacecraft up to a point that we could observe or track the asteroid up to, 17 kilometers away. So we still have a huge safety factor in, and could theoretically perform this slew with only 3 of the 4 available reaction wheels, having enough redundancy.
Okay, I think Yanis, you had your hand up.
I have many questions, but I could go with one at the beginning. What, like, as you said, you don't have the funding yet, but do you know who's going to make the satellite? Because it's a more or less, let's say, deep space satellite, and there are only like couple, maybe a bit more players who can actually pull off a reliable satellite. So do you have any information, or can you even share that?
So first of all, the previous, like the chair that I'm at, has already experience with building satellites themselves. So we have like 2 satellites flying in space already successfully. So there's some expertise in that. And then we try to get as many parts as possible as components off the shelf. And the thing we will do mostly is qualifying them to be deep space capable and adding some spot shielding if necessary.
So are you planning to do tests?
Yeah,
for the
there will
radiation
be
before?
a large testing campaign.
Can you a bit detail more your imaging strategy? How many pictures you want to take, and if you can show the slide you was discussing it.
This one, or?
Yeah, did you consider what will be the smear, for example, in pixels? Will it be below 1 pixel, or?
Yeah, so in principle, with this exposure time, this 0.05 milliseconds, there will be no observable blur, especially if we are able to track.
Yes.
And I think we are able to track, if we do the proper optical tracking, we won't have blurry images until like 10 milliseconds of exposure time, considering a drift of like, I think 0.1 degree per second drift. And I consider an image blurry if we have like a shift of more than half a pixel.
And how many pictures you aim to take in total?
Currently, we have a minimum requirement of 10 images. The expected amount is like at least 10 FPS image capturing. We obviously aim at more, but we still need to figure out whether this is achievable with the hardware. But we need at least 10 FPS to do the optical tracking properly.
And how long duration will be your slew maneuver?
The slew maneuver will, like the section with the 10-meter resolution, like the bright yellow, is like approximately the time that we are at slew rates exceeding 1 degree per second. So this is really just a short maneuver, but we will start observing the asteroid much earlier. So I think I mentioned it in this slide here. So we expect an observation time of almost 11 minutes, where we say that our pixel resolution is much more than just 1 bright pixel, but that we can see the asteroid with at least 5 pixels.
So you will make like 1 picture per minute if you aim for 10 pictures in 10 minutes. Is it correct?
Now
cadency?
The goal is to be at 10 images in this bright yellow frame. Like in this sections we want to have at least 10 images. Obviously we want many more, like we are currently calculating with 75 gigabytes of data. So we expect much more than that.
Okay. Can you just put the camera slide? I will just look it when somebody else gives a question. Thank you. Thank you.
Yeah, so Apophis is a relatively large object coming pretty close, at least on the sort of decades time scale. There's nothing else quite this big coming quite this close, right? So does your flyby experiment here, does that scale to, you know, if there's a smaller object coming close or a big object coming further away, like closer to the lunar distance? How would this work for YR4, for example, if someone wanted to do something similar?
Yeah, so we started to looking into that as alternative options, and that's definitely feasible. However, depending on the mission, we would need to adjust the propulsion system mainly, since at the moment we are at a chemical propulsion system, which is used to get us from GTO to the final orbit. And if we were to going further out, we would probably need to switch to an electric propulsion system. Otherwise, we don't have enough space and volume inside the satellite. However, for this mission, we couldn't choose an electric propulsion system due to the time constraints and the necessity to have really precise orbit maneuvers to accomplish our goal in this discrete number of orbits we have before the flyby. But in principle, everything on the system that is like in this upper half, it's like an 8-unit system. And if you wanted to, you could exchange this propellant section for a, I don't know, 4-unit electric propulsion system and fly it as a 12-unit system, or extend it further. Like, this would be like a system-specific modification.
Yep. Then this probably complements maybe the last question, but you have 3 years for Apophis, and you're in phase A.
Exactly.
So what's the cutoff to actually reach Apophis, to actually manage to engineer a satellite?
So if we don't have the funding by end of February, the mission won't fly. That's a fixed deadline, so this is basically the last presentation before this decision is made. And whether you hear from us in the future depends on this decision.
Do you have any prospects?
Not really yet, but we are still working on it. So
there's still like 4 hours to go.
Indeed.
Good. I'm very glad we had such a good discussion session. Less presentations, more discussions. Let's go. Any other questions? Yeah, okay.
Okay, Henrik Kampa, University of Tartu. So, okay, you have a magnetometer, but this mission will fly inside the magnetosphere of Earth, and so able to get the magnetic signature of the target itself. So, okay, to me it feels like just adding complexity to a mission that is really challenging to implement in the first place. But you have like a strong science case for including the magnetometer.
Yeah, so at first when we started thinking about this mission, we were considering that the end goal is to have a deep space capable spacecraft that is able to perform complex payload operations, to be able to in the future fly to other asteroids much further out. So we wanted to have a system that is from the start able to support these kind of systems, and which is why this mission is primarily a technology demonstration with a lot of really interesting payloads.
Any more questions? Oh.
Well, my question is a bit two-part question about the orbit. I don't have really a gut feeling, but maybe a bit of a fear about like when you were talking the orbit maneuver for approaching the Earth, that it would, you know, even go straight into atmosphere or have these multiple passes. Have you thought about what would happen if the satellite starts to like partially disintegrate, because you still have this GTO trajectory, and if it breaks apart and then part of it goes back into GTO, what would
This
happen?
is why we have this one perigee maneuver where we set our re-entry below 30 kilometers so that we can definitely avoid having this orbit hopping and disintegrating mid-space. Furthermore, we are doing simulations on that. For example, we use the ESA drama tool to avoid exactly this situation.
And I saw you, like you even have here the SDK simulation, this result. Does it take into account other satellites? Because right now you are crossing so many altitudes.
Yeah.
And have you added all these?
As of now, there is no real reason to add other satellites yet, because since we don't even know the launch date, the exact one, and depending on that, our orbit position could be completely different, and which is why detailed analysis is not feasible yet. We have propellant reserved for orbit evasion maneuvers, because we are certain that we have to do them from time to time. But we hope to, at least in the geo-orbit, avoid these collisions by just going 2 degrees off to avoid like the main ring itself. But yeah, in LEO or even the medium Earth orbits, this needs to be considered on an individual basis if it comes up.
Okay, thank you.
Okay, I'm not going to ask if there are any more questions. I think there are plenty. Oh, there's one more. Okay. We have time.
Yeah, because one talk was, there was this Alessia about lunar flashes. There was some schedule misunderstanding, so either she will join in a few minutes or we will have it at 3 o'clock after the last session, last talk of the first afternoon block. So she might join during the question, if not, 3 o'clock. So go ahead, we have time.
Due to the scheduling, I missed the first part of this presentation. But so you add 5 millimeters of shielding, so you
Exactly.
You come up with 30 kilorats for the electronics.
That's what we aim to set as a tolerable factor, yeah.
Yeah, but if you look at the orbit, if you're in a GTO, especially with a low perigee, there are 2 issues to consider, I think, and that's mainly the proton radiation that you collect in the low of an Allen belt. And second thing is that there are some components that are on the exterior of your satellite, like sun sensors or star trackers or whatever. And how do you handle the proton radiation and the radiation for the external components?
So we were doing radiation simulations with the Spenvis tool by ESA, and we figured that the total radiation dose is still primarily electron radiation because we are only rather shortly in this lower half. Like the majority of the orbit we are spending really far out, so we are still mostly collecting electrons, and with 5 millimeter aluminum shielding, we basically reach an equilibrium, so the incoming or the residual radiation inside the satellite is approximately 50% electrons and 50% protons. So basically up to the 5 millimeters, adding electron shielding is more efficient, and from this point onward, proton shielding would become more efficient.
And the external components?
The external components are still a big consideration, and a thing we are still working on. Like, I don't know, having spare parts that are code redundant and potentially shielded with additional mechanisms, but this is something we still have to figure out, and will be shown in the radiation verification testing whether these components are suitable for this environment or not.
Any more questions? Oh.
maybe I missed it in the talk, but how precise of a launch window do you need? So since you mentioned that you're not the primary payload, so rideshare, you don't really decide on the launch date itself, let's say specifically, as you said, but how flexible are you from a launch window?
So we currently estimate that we have additional fuel to guarantee a 30-minute launch window each day. This is still really tight, but it might be manageable and depends on how strict the launch providers see the situation. Maybe we need to add additional fuel to increase the launch window.
And let's say not just on a daily basis, but like, you know, there is, I don't know, strong weather event that keeps you from launching for a week, or like how
This
long?
doesn't matter. Like, we have each day a launch window that is acceptable. Of course, we can't wait 2 months, but 1 or 2 weeks is not a big deal, since each day there's a constellation where our target trajectory with RAN plus argument of perigee aligns with the geo-orbit trajectory. So.
Okay, so basically just not be too late for Apophis, but
Yeah.
otherwise you're good. Okay, thanks.
So one more hand back here.
I had the same question, so I'm good now. Sorry.
Such a disappointment.
I mean, I really appreciate having that many questions. It
Yeah.
just means it's a really interesting subject here. And I really appreciate your participation.
Or if anybody has any question on the previous speakers from the morning session, feel free. Otherwise,
I think
there are no other questions. We have the plenary talk by Michael Peepers at 11:15 in Kaleva, and we will reconvene, I think, is it for 13:45?
yes, we reconvene.
13:45 with the session on the
Solar system exploration, small bodies.
exploration and payloads. And remember, at the 15:00 will be the talk which was missing today about the lunar flashes. So they will try to update the program accordingly. Okay, thank you. It was a good time.
Yes. Big round of applause for Jonathan.
in this workshop we are presenting for Mermaid project, that our last project was image prioritization for the Comet Interceptor mission of ESA. Yes, and we are doing it. They are using also 3D plus camera head, but older one. You have the newest one with a better FPGA. And yes, to reduce the data output of the camera, we developed the algorithm on FPGA and launched it that crops out region only around the object, in your case, an asteroid. And in the Comet Interceptor, in the optic instrument of Comet Interceptor, it is done directly in the camera head. When since they take image, they found the centroid of the object and cropped around it. And now maybe, how you are considering this image prioritization on the jet zone or something?
Yeah, our main consideration is that if we want to have everything done on the chip already, we also need to do the basically the optical tracking on the chip as well. So this is currently under consideration.
I mean, the FPGA should be powerful enough from what I've read so far. It's like in the 3D camera head, there is quite a powerful FPGA right now. So that's why it would make sense.
I'm unfortunately not an FPGA expert.
Yeah, as I said yesterday as well, me neither, but I heard our people talking about that already. So
because for this ESA mission, they have like quite outdated FPGA in the last variant of the 3D Plus, because it is not intended for the image processing, but still we managed to implement very lightweight, very simple algorithm, because it can be simple, because in most cases there is a black background and one bright object, and we can easily detect it. But no, maybe in some future you have some interest in FPGA-based image prioritization. We can share some insights how we did it, or maybe there is some collaboration. I can share my business card, because this is what we are. Our presentations in this workshop is about hardware development, but mostly we are doing FPGA firmware development.
Yeah, I was sitting in your talk yesterday and poster as well.
I'm curious, since we're already on the topic, I was also questioning that for your mission a little bit. Do you expect, or especially for Comet Interceptor, but probably less for Apophis, but still possible, not necessarily outgassing, but dust coming off, which could be, you see the asteroid or comet, depending on the mission now, sort of in the middle. Let's assume camera tracking is good enough, sort of in the middle of your field of view, but there's dust coming off, which could distract the windowing algorithm.
Yes, for sure. Dust, dead pixels or something.
Yeah, dead pixels.
Yes, the algorithm for the Comet Interceptor, since the FPGA is very constrained in that case, it is looking for the largest, brightest and roundest object.
Okay.
Yes, this is how it can be improved, but they do not have any resources on the FPGA. But in your case, you have like superior FPGA.
But the optical tracking we are currently doing on the jet is doing exactly that, like binning, contour search, go.
Okay.
And we are doing it on a Jetson at the moment because we have a satellite in orbit right now which has this capability and doesn't have an.
I mean, considering the timeline, also FPGA development has a risk of taking longer than if you have already a Jetson in space where you can test it. It de-risks the whole thing, of course.
This is a very significant risk. Yes, for risk. We were developing it's very simple algorithm, but it took us for 2 years for optimizing it, for optimizing the timings and all that. It was the development of the idea was quite fast, but all this tuning, it was.
There can be somewhere a small timing misalignment, and you can look for it forever.
Yes, and as in your speech, the automatization is key for this. To analyze the reports, to put all the documentation in automated, because what we are doing, we are rerunning like code coverage analysis and functional coverage analysis, so like extremely high amount of iterations, and it's crazy actually. Sometimes it's very painful.
That's why we have a job, though.
Yes.
You gotta always think this way around. That's why you have a job.
This is how I motivate my team. Yes.
If it would be easy, somebody else could do it.
Yeah. I mean, software is always very fun, except when you have to debug the same thing for and it's fun.
And yesterday I also wanted to approach you. It is maybe a specific question, but we are a very small company from Latvia, and for sure we have interest in the future to work with the big players. That we know that if you would write cold email, hey, here we are good at FPGA, nobody would answer on them ever. It is what it is, and we know. How you would suggest, how we can, for example, to approach, like, to get in some small parts in the DLR projects or DLR projects or something? What is
So generally now talking again about FPGAs, I guess.
Yeah, FPGA firmware development, not other
It's a good question, because I mean, for us, I guess it depends a little bit on the institute. For us, since we're also only having the FPGA, if we develop even one, as I said, like in the mission that I presented yesterday, we didn't do anything. We basically bought like the whole box from Airbus as a complete system, so we didn't even have any FPGA development. But if we're developing so if we need to develop the FPGA, normally it's not a standard application, because we're doing basically science stuff, and we normally have to integrate some science algorithm from people that, are let's say scientists that change their minds regularly during the development of the whole topic. You know how it is. So that's why we tend to not actually give that out to external companies, because for us it's really like, as in that case as well, the only FPGA there is normally the one that's directly at the sensor head. And then we don't do other FPGA anymore, let's say. But I think that would be actually a point when there's other institutes where there's, let's say in Bremen there is one that's more on space systems in general, that does more than just, so we're originally optical sensor systems. That's also why we were actually, as I just learned, apparently also involved in that work. At least a colleague of mine is involved there, because it's really just, let's say, very specific on optical stuff, optical sensors. But I guess in more general topics, I could imagine, because I know that often from DLR perspective, people, they're coming from the physics side, so they're developing the actual sensor, which is not the case in our case, but for the other institutes it tends to be rather that way. But they're not too, let's say, they don't have too much experience in the whole data processing stuff in the background. And I think there it could work better for you actually, that when you see that people actually, they're more, let's say, they have better focus on the actual sensor technology, because they're coming from the physics side, let's say. There they tend to not have the expertise on the FPGA stuff, and then they try to externalize that even. But I guess there it's it's actually in events like this here, so with conferences, getting to know people, because I mean, I know you. There's so many emails you get from companies all the time. I even also ignore sometimes the big ones, because it's like, why would I care if I know I cannot pay for it anyway? I cannot give it to externals. Like personal contacts like this make sense. So I suggest their conference, or if you want to give me your business card, for sure as well. As I said, I don't think there is much for us, because we're a specific case. But I mean, there's also other institutes where I know, for example, they're doing, I think that's Hannover. I'm not really involved with those people, but
there is one thing we can offer. We can pay for ourselves via national ESA projects.
That's true.
This is
that's
our
true.
main
That's also, that's still a good selling point, and that's especially, so we have let's say, the luxury. We're doing space projects since long time, so we have basically a lot of expertise in-house. But that's what I just wanted to say. I know that there's a group that started 2 or 3 years ago that's working on, I think they're doing something with laser and laser ranging, something like that. But they're a rather young group, and they're coming from the physics side. So they know the laser technology, they know all the front-end technology, but they do not know how to process, anything behind that. They even approached us for, could you maybe think about developing the software, because they don't have any software expertise whatsoever. And I think that would be sort of a target customer. I mean, not maybe specifically that group, because since 2 or 3 years they probably already started looking into it, but that, like, the kind of targets as a customer that would be interesting to you, like the research groups that do the actual sensor, that like develop the sensor technology themselves. They tend to not necessarily care for what's coming behind of it, let's say. And also considering your talk yesterday, I mean, that would fit in the sense that they would be the specific part, the proximity electronics part in the front. That's what they can do, that's what they know, and all the rest they often don't have expertise. And there they might be very interested in saying, okay, maybe there's somebody who can do that for us without us needing to do anything.
I think there's one thing that increases the chances that you get contracts with DLR, and this is having an office in Germany. Because oftentimes, or based on my experience, if you have like a DLR funded project, they are interested in keeping like their investment for the university in the German industry.
Depending on, yeah, that's true actually. I mean, that's for the whole European space business. In the end, it always has to have an office in the country where the money is coming from. But that's also why it's interesting if you can say, okay, you're going where you can provide funding for yourself to at least some extent from ESA, then that actually helps as well.
Yes, because we have some like collaborations that we can get some, the main funding we get for us as a prime contractor, and maybe also some very small funding for the partners to define the requirements or something. So it's not really extra overhead for them.
I mean, what we also gave externally once was actually not the space-related stuff, so that depends a little bit on how focused you are with your company. I didn't really check the webpage or anything. But what we've given, for example, to actually a research institute, but still in Brazil, was basically a camera simulator that we have, or emulator that we have in the lab to test our whole system, where they did the complete like software and FPGA development. But because it's not flying, it was easy to keep it externally. I mean, specifically Brazil, because they're not even a European country, so for an ESA project, it would have been hard to give anything that flies in space to, again, because of the argument it needs to somehow stay within Europe, it would have been hard, but like this ground support equipment is very easy to externalize because their requirements from ESA are very much lower. So there it's a lot easier, or the barriers are a lot easier than for space-related hardware to enter the game, let's say. But of course that changes the focus a little bit for a company, of course. So it depends. It's just also something to keep in mind that tends to be easier to be done, to be externalized. Yeah, I would say. But yeah, I'm sorry I cannot help more. But
okay. It's nice to have your insights. So it's lots to understand because, frankly speaking, we are more or less engineers, and this business side is not so easy for us.
I totally understand. Yes, I totally do.
I guess we have to go.
We have a meeting.
Okay. Yeah, but yeah, exactly. So, thanks for that. Yeah, have a nice day. And if you still feel like it, presentation at I think 4:35 today.
Okay.
Yeah, we will be here.
Yeah. I think 4:35. Yeah.
Like we should. Okay, yeah, 2, 3. Okay, so then I will not skip the introduction. Okay, but anyway, OPIC. So yeah, this is what it looks like. So it's not that this big in reality. It's like this size. But okay, last year on the University of Tartu booth, the Kuukulkur lunar rover took all the attention. So because OPIC is small and they are moving. So this year we made a bigger version of OPIC to get some more attention. So this is, I will be bringing it back to the booth after this session, so you can have a look at it. Yeah. But then to the actual topic. So yeah, the background of Comet Interceptor. So, Comet Interceptor is a ESA F-class mission that will fly by an object that is visiting the inner solar system for the first time. So, yeah, probably that will be a long period comet. But if you are really lucky, then we will might be able to intercept a interplanetary object. Okay, in the morning session it was mentioned that to reach an interplanetary object you have to have a big delta V. We don't have that, so it's unlikely that we will succeed. But yeah, let's hope for that. It will be, of course, even more super interesting than having than flying by a long period comet. So yeah, the mission profile. First of all, Comet Interceptor is the first ever planetary exploration or solar system exploration mission to be launched before its target has been found. So the launch will happen in 2028 or 29. Now it seems more probably 28. And then the spacecraft will be fly to the L2 point and will be waiting there until a suitable target object is found, and it can wait there for up till 5 years, probably even longer. And then try to fly by this target object and yeah, so okay, this 32 is of course just an estimate if it's find at that time. So yeah, the spacecraft or the mission is composed of 3 spacecraft. So there is spacecraft A, the main spacecraft from ESA, and then 2 smaller spacecraft, B1 from JAXA, the Japanese space organization, and B2 from ESA. And there's 2 smaller spacecraft will be separated about 1 and 2 days prior to the encounter and perform flybys closer to the object than the main spacecraft. Yeah, so here is a simulation of this. So it will be a multi-spacecraft flyby. Okay, this video is really old, and the spacecrafts actually don't look like that. So, yeah, but it was the best I could find. But okay, then what comes to the instrument itself. So OPIC stands for Optical Periscopic Imager for comets. It's a monochrome visual range camera. And yeah, it will be on board spacecraft B2. So we have here a mechanical model of B2 actually on a shaker bench, and here is the mechanical model of OPIC. Yeah, and so it's directed so that it takes images in the direction of travel. It's provided by the University of Tartu, and that makes it the first Estonian full participation in the ESA science mission. Yeah. So OPIC is the field of view is this 18.3 to 80.3 degrees, and it's tilted by 8 degrees with respect to the rotation axis of the spacecraft, as shown in this image. Okay, I will explain soon why. And yeah, why do we have a periscope? So we are actually looking to the side, but then we have the mirror here so that we are looking in the direction of travel. Okay, so we are flying by close by a probably active comet. So there are all kind of debris around. So we don't want them to have any direct hits on our optics. So that's why we have this mirror here, so that if we have something hits us, then it hits the mirror and not directly the optics. So yeah, this is what the instrument looks like. Okay, open one side panel open so you can see inside. So yes, here is the mirror I already mentioned. Then we have a optical filter. So making sure that we are seeing the same optical, same wavelength range as the comet camera on the spacecraft A, so we will get comparable images. Yeah, optics you don't need, of course. Then we have the CMOS imager So the resolution should allow us to detect less than 400 meters per pixel resolution from 400 kilometer distance. And this FPGA, so this together form this camera box is actually the 3D plus camera that was mentioned already in the morning session. And yeah, then interface electronics to connect with the NVIS instrument. So we are like commanded through them. Okay, there are no presentation about that, but we are not connected directly to the spacecraft, but we are connected to another instrument that is controlling us. Yeah, so here's an animated field of what the animated image of what the field of view of object would look like, and this is the reason why we are not looking exactly at in the direction of travel. We will, when the spacecraft rotates, our view will scan a larger area around the object when we are not looking directly towards it. So this is what the, okay. So this video that you just show, that I just showed, I didn't make it for this presentation. Okay, I actually personally didn't make it at all. So it was made actually for this test, this full functional test. So yeah, this is a rehearsal. As you can see, this is in a normal room. This is not a clean room, and indeed we have only the optics here and a breadboard. Camera systems here, so it's not the real flight system, but this is like the idea of how we like test the end-to-end functionality of the system. So yeah, the spacecraft is rotating, but it's much easier to make the image rotate than to rotate the system while testing. So that's why this is the test is done this way. So yeah, science data that we will produce. So the first will get this kind of full frame images when we are far from the object. And the 6 of these images will make this kind of full cone sets where we scan the whole area around the object. Okay, so these are images from the test that I just showed. So they are a little bit ugly, but remember this is raw data. I just wanted to show it, to showcase that we actually have test data instead of some nice simulation. So the real okay, there's also vignetting that comes from the test setup. So I can ensure that the processed data, flight data, will look better than this. Okay, so these images are used to characterize the gas and dust around the object. Okay, then when we will come closer to the object, so this is what the view will hopefully look like. So we can see that the object is really going through the field of view quite fast, and most of the images will just be dark sky. And because we have because we have, of course, a limited data link, it's not a good idea to just downlink images of dark sky. So that's why we have this onboard data prioritizing and cropping system developed by BitLake Technologies. We have, by the way, Yanis from BitLake in the audience, so if you have questions about that, so ask him, not me. So yeah, so the thing that this, but okay, so what this system does, so it basically crops the object itself, and all of these cropped images are then downlinked. And then together with the images of the spacecraft A, then these are used to construct a 3D model of the object and its dust jets. So, yep, some images of our tests. So here we have the shock test. Here done by Rauno, who is also in the audience. So yes, at the moment the flight model assembly is going to start. Okay, here I said it started, but okay, it's going to be started very soon. And the delivery is okay April 26. I think the official day in May, but I think we can be faster than that. Okay, so the team. So as you can see, first Estonia project, but there are also people from Latvia, Lithuania, and me from Finland. And our main contributors are Crystal Space from Estonia and BitLake Technologies, as already mentioned. But okay, I think I have, how much time do I have? 2 minutes? 2 minutes, okay. So then I maybe explain this anyway. So why, okay, we are called OPIC. Okay, it's optical periscopic imager for comets, but actually the name comes from Ernst Öpik, who was an Estonian astronomer, and he proposed the existence of a reservoir of comets in the outer edge of the solar system. So nowadays this is known as the Oort cloud, but indeed Öpik proposed its existence before Oort, so it should be called the Öpik cloud actually. Yeah, the target object will probably come from the Öpik cloud, so yeah, that's why it's called Öpik. Yep, and in the end I have a video made by Sten, who is also in the audience. But you can ask questions during the video.
Okay, yes, we have like time for like one quick question, I think. Anybody?
Everybody's just looking at the video.
Yeah, you can also look at the video in principle. It would be weird for me to ask questions because, yeah, you know. Okay, so I guess there are no questions. Well, it has to be very short, yeah.
All right, let's have one question. And on the PAQA, so what part has been the most hard to test and qualify on the requirements side? Because it's quite an interesting device.
Indeed, the optics, because they are commercial optics. Okay, there have been many challenges, but this verification of the optics is actually still going on, even if you are just building the flight model. So, but okay, based on everything that we have done, we are sure that they work, but still the official like verification program of the optics is still going on. So making the system stable, the optical test bench enough stable so that we can do one test and be sure that the results are repeatable. It was a big job. And actually, Mihkel solved this problem, so thanks to him. Yeah.
Okay, so we have to end here now. So, and welcome our next presenter, Antti Näsilä from VT2, who is the co-lead investigator, co-instrument lead scientist from IRMIS on Comet Interceptor. Yes, exactly this one.
Okay, hello everybody. Do we need mic for the online people? Okay. So let's try to make this manageable. So hello everybody, my name is Antti Näsilä, working as a principal scientist here at VTT and also as the co-lead scientist, whatever that means, of MIRMIS instrument, CoPI in normal ESA language or space language. And I'll tell you about what's the current status of the MIRMIS instrument for the Comet Interceptor mission. And luckily, Henrik already told you about Comet Interceptor because I did not prepare any slides about the mission. But MIRMIS is a joint instrument from Finland and UK with also scientific contribution from the US, from NASA. And we are on the main spacecraft, spacecraft A, and the OPIC was in the smaller probe B. We have sort of three scientific instruments on board, thermal imager from Oxford University, then we have a mid-infrared point spectrometer from VTT, and also then near-infrared hyperspectral camera from VTT. And the goals are to, or objectives are to answer questions about the composition and the environment, maybe evolution of the comet. And we are covering quite broad wavelength range from 900 nanometers, so which is near-infrared, all the way up to thermal to 25 micrometers, so very, very broadband instrumentation. But for us, the main role is in the near-infrared from 900 nanometers to 1700 nanometers, and this is exactly basically an exact copy of the infrared channel from aspect instrument on Milani CubeSat on Hera, about which Thomas Kohut will talk in this session later. But anyways, it's single interface to the main spacecraft and commanded through the Oxford data handling system. And currently we are building the flight model after many difficulties, but it's ongoing. Here's a sort of overview. It's maybe, Thomas, do we have the MIRMIS somewhere in the building? This is the STM, it's about maybe this size, so it's actually quite small. Okay, so what it contains, just quickly, bad old slide, but it's like, well, we are commanded through the main spacecraft and there's the data handling system, but due to the interface speed from our side to the Oxford side, we also have like a complete independent operation in our imager, so we can do long-term data storage also on our NIR channel. But what we have scanning mirrors for both sides that we can actually track the comet, because somebody decided that we don't want to turn the spacecraft. And then there are two cameras, and both have their own telescopes, and they are, during the flyby, they will record their data and store it on board, and then sometimes later it will be downlinked to the ground. Both sides also have their internal calibrations, so during the wait in the Lagrangian point we can perform instrument calibration, or not calibration, but calibration checks that if there's some drift or something that we can then correct. So it's quite well packaged. Okay, so where are we? So this is from the Oxford side, so the thermal infrared imager, so all parts exist, are ready, have been baked, prepared, so now the actual integration can start. Some nice photos from the actual flight hardware. I don't explain what they are doing. PCBs as well, so on the Oxford side and the data handling system, all the PCBs are ready and assembled, so just waiting for the instrument integration and EMC testing this spring. So all the parts exist for the thermal infrared side and the data handling system, so that is progressing. Then on VTT side, our optomechanical assemblies are proceeding, mostly even completed already. Spectral filters for the mid-IR being assembled. near-infrared spectral filter is ready, waiting for the electronics integration, or that's actually happening as we speak. But the problem is our main electronics, so the assembly of those, or the population of the components on the PCBs, that's pending, and it's out of our hands because it has to be, or we had to use a ESA-certified subcontractor, and there are some delays on there, and we don't actually know when we are getting the PCBs. So planning is a little bit difficult. But in parallel, we are also integrating an EMC test model that's fully flight representative, but not with this kind of space-grade assemblies. And hopefully we are running this test in March-ish, maybe, by current estimation. But that'll be sort of the final test that is needed for the sort of system acceptance. Then, of course, there will be acceptance testing of the protoflight model, but that should be easy because the STM already passed all the vibrations and etc. And there's also at the same time happening a radiation test talk about our detectors, but that also was quite illuminating. Some pictures from the spectral filter assembly. So like I said, the optomechanical assembly is complete, and now we just need to add the electronics to the module, and then we can start actually calibrating the spectral filter for the NIR channel. All the optics are assembled. From lessons learned from Aspect is that we had to add some extra stray light prevention in the behind the it has exactly the same optics design as in Aspect for Hera, but we added some extra sort of black stuff to prevent any stray light, and according to simulation this will significantly improve the performance from that. But everything is already assembled and waiting for the integration. A few words about the near-infrared detector side and the FPGA architecture. It's quite hard to read, but I'll try to walk you through it. So basically, well, similar to OPIC and probably every camera, that we have our image sensor, which is our data source. From that, we need to control it somehow. Then there's the actual data stream handling that we need to dump into a RAM or like a short-term fast memory. Then from that, we have a block that actually reconstructs the image because it's just a messed up bunch of bits, and there's no real image as it comes from the image sensor. You need to reconstruct it to have it something human readable. But we are doing that also in real time inside the FPGA, and then storing it in our long-term storage in the flash. And everything's handled by our own FPGA, which also interfaces with the microcontroller, which then interfaces with the command and data handling system. And this has been tested in our setup end-to-end, so everything, image acquisition works. It can store to RAM, flash, and also transmit over the UART. But here's a nice caveat that it takes about 14 milliseconds to store the image to the RAM. From the RAM to the flash, it takes 140 milliseconds, but then from flash over UART to the main computer, it takes almost 100 seconds, so it's 1,000 times longer. So we can't actually use this to calibrate the instrument because we need to take thousands of images during the spectral calibration. So we need to sort of hack this and directly hook up somewhere here to transfer the images to our computer at higher speeds. Luckily, in the full instrument testing, to verify our calibration, we don't need to transfer full images. We can just take small slices, so that'll then speed it up again. But yeah, these kind of things that you don't, in normal world, you don't run into these kind of problems. So when doing space stuff, then you realize that these interfaces are actually extremely slow. And it's not USB 3. It's not even USB 2 or 1. It's like modem times. Image sensor, I'm running out of time. Selection for the image sensor, so we had procured in the project 3 detectors with equal specs, but as we can see, there's quite nasty differences in them. The dead pixel count is more or less the same in everything, so it's in spec, but in at least, especially one sensor, all the dead pixels are in the center, which we want to use. So no good, but then the other two were more or less okay. And but then we have selected actually this one for the flight detector and this one for the flight spare. Then a few words about the spectral performance. Maybe I'll skip this. So we have selected, well, you saw it, it's existing, but and here also we can operate in two different modes. So we can have this sort of signal interference order for low light conditions, so it's a little bit broader. Here's this second plot shows the spectral resolution or transmission bandwidth as a function of wavelength. So if you just use the lower interference order, then our spectral resolution starts from 45 nanometers and goes down to about 32 nanometers. Our requirement is 30, so this doesn't actually meet the science requirement, but in case, because we don't know where we're going, if it's very dark, then it might be better to actually have some signal instead of nothing. So, but in the nominal operations we can use 2, and there we can, except for this region, we can meet the requirement for most of the wavelength range. For the mid-IR, here we had a nasty surprise that probably due to the sapphire needed for the substrates, it's behaving much differently in temperature as the other channel, and we noticed that we are losing quite a lot of, well, now I don't have time to explain this picture, but we are losing a lot of operational range when we go to minus 40 degrees, which is our nominal operational temperature. But we came up with a mitigation mean here that we can use actually the higher interference orders to cover the necessary science wavelengths. It'll be a little bit more complicated to use, but at least it seems that we can do that. And one probable flight model has already been completed, other 2 in assembly today, but we still have parts available for 10-ish if needed. We don't have time to make 10, but we could make. And then there was also detector interference that we found out quite late in the program, but luckily we managed to solve quite quickly. That we found a place which can provide us flight grade PCBs with 4-day turnaround, and we sort of removed the problem. So here you can see that this kind of our chopping, we need to chop the detector, but that created an error at the chopping frequency, which saturated the detector, which was no good. By changing the electronic scheme, we managed to remove that, but introduced something else. But then when we got the final PCB, everything was sort of removed. And now I will skip the, well, okay, this is almost the last slide anyway. So next steps are EMC, integration, calibration, full instrument integration, calibration, then delivery maybe at the end of summer this year. Yeah, I believe you can read that.
Okay, thank you. I think we can take like one quick question, if there is a quick question. No questions apparently. Then we can, move. Thank you. Again. Our next speaker is Kristaps Blumbergs, who is both from Riga Technical University and Ventspils University of Applied Sciences, and will be presenting flyby visualizations for Comet Interceptor. And I will give you this also.
Yeah, thank you. Is it working? Oh, it is. Yeah. So, hello everyone. My name is Kristaps Blumbergs, and I'm a first-year PhD student at Riga Technical University, and today I will talk to you about how we visualized realistic flyby trajectories for the Comet Interceptor camera instruments in Blender. This was a part of my work for my PhD, as well as this was a project for Ventspils International Radio Astronomy Center. The objective of this project was to develop a pipeline that would generate a flyby scenario based on user input for a selected instrument's camera and visualize the results in Blender. As well as we would use SPICE kernels of discovered or known comets and their trajectory positions to simulate virtual targets. This would be a nice intro to the mission itself, but this was already well explained, so I will skip this for now. Our goal wasn't to create or develop a camera ourselves, so we took inspiration from the Comet Interceptor instruments, specifically from 3 different cameras, 2 of which were optical, of OPIC and ENVIS from probe B2. And we know, and lastly, we also took inspiration from MIRMIS. But we realized that this isn't an optical instrument, but we chose this to more so simulate different ways how the camera could move in 3D environment. I briefly mentioned SPICE kernels previously, but if you're not familiar with what they are, these are essentially data sets that hold information of ephemerides of target bodies. They have information for instruments, specifications for reference frames, and this data comes in different formats. For example, the way how ephemerides are held in a SPICE kernel is in an SPK kernel with a file extension of .bsp, the B signaling that it's a binary kernel. There are leap second kernels that help to calculate at what position a target body is at a certain time. And there are a bunch of other different ones, but to use these datasets, a SPICE toolkit is necessary, and in the case for Python, SpicePy wrapper exists. We developed, or we made a lot of input variables that the user can change, and for starters, these 4 are the most important ones. Trajectory start and end, which would make a time frame where we would gather the positions of the L2 and the comet. Steps essentially divides that time frame into how many positions we would get. Comet name, it's kind of self-explanatory, but we can also, we can define the name and the SPK ID, which is from the knife database, which holds all of the information about comets. So these are variables only for just defining the trajectories for the L2 position and the comet. And there's a little bit more that we can define for the flyby itself. There's more to it, but I didn't include that but these are the important ones. Closest distance is just the distance necessary to imitate a spacecraft launch, to say. This would be as soon as the distance from an L2 point to the comet would be lower than what the user defines, we would imitate a launch. Closest approach is the closest distance from spacecraft to nucleus during flyby. Flyby duration, it's the duration in seconds. But if we were to take this into a Blender, by default, Blender has 24 frames per second. And if we were to define 60-second flyby duration, we would get 60 times 24 amount of frames. Camera, we can choose whether we want OPIC, ENVIS, or MIRMIS. Rotations per minute, this is only for probe B2 because MIRMIS itself doesn't rotate. I hope I was right there. And lastly, we can define the velocity of the spacecraft. To understand how this works a little bit more clearer, a diagram. I'm not going to go into full detail of all of this. There is an image helper right here that will help me explain. The blue lines show the positions of L2 in a time frame, and this is the comet positions, and this is the SPK ID that I mentioned before. The workflow consists of three main parts, where at first we would gather just the positions of L2 and the comet, and then if we were to imagine that this and this point is the starting positions in the time frame, we would go through all of these positions, and as soon as the distance between 2 points would be lower than user-defined closest distance, then we would imitate a launch. Then for every remaining position that we have for the comet, we would calculate where the spacecraft would need to go, taking into account the closest approach distance that was defined by user, and we would calculate whether or not the spacecraft can make it there in that time frame. If the distance to that point is sufficient enough, then we will set up the Blender environment. We will put in all of the camera positions, the rotations, the same for the comet, use an existing nucleus body or of a 3D model, and based on which camera was chosen, we would add either a tail model for ENVIS or command jet model for OPIC or MIRMIS. These models themselves weren't developed by me, those were developed by my colleague. If you're interested in seeing more details about it, he should have a paper published sometime this year. If not, I can give you email to contact him directly. Forgot if I mentioned one thing, but these would be the flyby results. Just like previously, the blue line is L2 and the yellow is the comet positions. For this plot over here, we chose 3i Atlas in this time frame, and for the plot on the right side, it's it is a comet positions, much like the previous plot, but this is 17p in these time frames. I realized that in the title there was realistic trajectories, and you might notice that there is a completely straight line going from this point to the flyby point, which probably isn't that realistic. But this is the approach we chose because we just needed to get to this point, and this was a sufficient enough approach to get to the end results that we wanted. Then if we were to zoom closer on these 2 points, we would get flyby trajectories that would look something like this. These are just 3 different views taken from the same plot. On the top side, we chose OPIC instrument, so we took 200 kilometers of closest approach distance. There is a gap between these lines. This would somewhat signify that there is that 200 kilometer distance between that closest point, and the spacecraft velocity was of 70 kilometers per second. This was for the 3i Atlas, and this one is for the 17p. Again, same velocity, but for this one we chose MIRMIS, and that's why this closest approach is of 1,000 kilometers. For the next slides, if we take just a little bit of a look on these flyby trajectories, they're kind of perpendicular. If these points are kind of close, and for OPIC, we realized that this distance is kind of too close in order for OPIC to get any results. So some tweaking was necessary to get the results that's going to be on the next slide. But I already was told that this, if we just take account that this point is just rotating around in one specific side of the image, then this would be okay, but this is rotating a bit differently than expected. But this would be the result of OPIC. For Mirmis, this is a 2-minute render sped up 4 times, where we're getting closer to it, and at one point we would be able to see the comet itself, and there's a jet coming out of it. If Mirmis was an optical instrument. Okay, yeah, for ENVIS, the results were a little bit different, and we're not really sure how this was supposed to look. But my colleague Gintz, together with Mario, who was working on asteroid image simulator, got a result that ENVIS team was happy with, and it would look something like this. To conclude, the trajectory-based approach works as a good proof of concept for creating flyby scenarios for virtual targets, and it allows for a variety of different flyby scenarios. And while Blender allows for a straightforward setup of optical cameras, additional effort is needed to make the resulting visualization resemble, for example, near-infrared data. Future plans, I'll just quickly thank you for attention. Do you have any questions?
Yeah, thank you for being in time. Any questions from anywhere?
If you have any questions off of this or opinions that you would like to say, feel free to come to me. I'll be here.
Yeah. My question is, what are your follow-up plans with this actually currently? So do you have a follow-up project already secured, or you are planning on doing next phase of this study?
The plan for the future, which I kind of skipped that slide, was that pipeline only uses existing comets and their trajectories. The plan is to make a workflow that would create spice kernels and generate random parabolic or periodic trajectories that would be helpful.
Okay, thank you again. Yeah. And our next presenter is Tomasz Kuhut, who is currently at University of Turku, right?
Yes.
And who is the PI of Milani CubeSat for Hera, right?
Okay, hello, I'm Tomasz Kuhut. Yes, I transferred to University of Turku, but actually to city of Pori campus. And I am PI of the Aspect Hyperspectral Camera on the ESA Hera mission. And we have exactly 1 year to the arrival to the asteroid and actually deploying our camera. So, Michal Keepers in his keynote talk gave some introduction to Hera. But what is it actually about? Hera is a planetary defense mission, and the objective is to characterize asteroid response to a kinetic impact, if we can deflect or change a trajectory of an asteroid. So a couple of years ago, a US DART spacecraft impacted a small asteroid called Dimorphos, and it's part of a binary asteroid system, Didymos-Dimorphos. So Dimorphos is orbiting a bigger Didymos. And that impacted it head-on, and it had 12-hour orbital period, and the impact slowed it down by half an hour. So it was actually quite effective. A lot of debris was released, but we don't have post-impact images or characterization only from ground-based telescopes, because the DART did not survive the collision. So ESA is sending a Hera spacecraft, which will characterize the post-impact shape or state of dimorphos, and also if some material was ejected and impacted Didymos. And Hera was launched in September 24, so 1.5 years ago. In the spring, it did successful Mars flyby, and it's now on the way to Didymos, where it will arrive in October this year, so already in a couple of months. And Hera has also 2 CubeSats for a more close-up observations, and one of them is called Milani, and it has a Finnish Czech-built hyperspectral camera called Aspect, operating in 650 to 2500 nanometers. It has 4 independent channels. 3 of them are imaging. You see the resolution here. And the shortwave infrared is just single-point spectrometer. And the hardware was built here at VTT. And it has a special spectral filter, which is a tunable Fabry-Perot interferometer. So the wavelengths which it images are not predefined, but you can basically tune the filter to any wavelengths within the range of the channel. So you can flexibly change it in flight. And with that, we want to actually map both asteroids because it's an imaging spectral instrument, for example, to identify minerals and their abundance and if it is changing on the asteroid. So this is an example how it would look like on a Itokawa asteroid example. So we did already some tests in flight. Unfortunately, we don't see with the Aspect any light from outside because we are inside the CubeSat deployer and the doors are closed. But we can do some functional tests. So we did already last December a test of this Fabry-Perot interferometer through collecting housekeeping data, and here you can basically see that if we command the spectral filter to change to different wavelengths, we see a response. Those are these steps, so the spectral filters work. Everything is fine. And we also 2 times acquired so-called dark images to check the noise levels and the fixed and random noise component. And then you can see here, everything is fine as expected. This is basically the dark noise level, the background level, and this variation indicated by the error bar, standard deviation of the signal variation, that's the random noise component. And we see that if we take repeatable pictures, it's quite uniform. This is the visible channel, this is the near-infrared channel. First value is somehow shifted down, but we know it, it's an issue. We always have to discard the first value, but otherwise if we repeat the measurement, everything is fine. And the random noise component is just few percent of the background fixed noise component. So it seems to be fine, and it's actually slightly better than what were the tests done on ground because we are operating at a bit lower temperatures, but there is no damage, everything works fine. No additional electrical interference in the spacecraft. So what still we needed to do or need to do? So before the launch, there was done a calibration of the instrument and there was a big bunch of data collected. It was done by the team from the Budapest University of Technology at ESA ESTEC just before delivery of integration of the Milani into the Hera spacecraft and shipping it to the launch site. And we, through the year, last year, did process the calibration and we think everything looks quite fine. So here are examples of the flat field images. The maximum variation from the dark blue to the yellow is 20%, but in the central part of the image we have variation less than 10%. So it's quite uniform, it's steady, it's repeatable. We can correct the signal magnitude for the flat field. Here is example of the geometry chessboard pattern, and again it's the distortion is maximum to about 1 pixel geometric distortion. So the optics are of very good quality and the image is drawn pretty well. So that is done, but when we have the calibration data, we must also apply them on the raw readout images from the instrument. So we had to do so-called ground data processing pipeline, where we apply all the steps of the calibration onto the raw images to produce a calibrated images. So I will again show you some examples. That's an example of actually aligning and resampling of the images. And we have an algorithm which, for example, identify if we take this is extract from a single pixel at the different spectral wavelengths in the range of the instrument. If we want to scientifically process the data, we must remove some outliers, remove noise. So in red or in green, here is some noisy data, mainly in the visible channel, which we must smooth. And because we have different channels, so they might be a bit offset. So we have to connect also the segments to get a resulting smooth spectral curve, which is here in blue. And once we apply all the calibration and also the corrections of the data, we can come down to scientific data products. So for example, produce albedo maps or spectral slope map or band depths of mineral absorption bands. And then we have also machine learning algorithms which can extract, for example, which asteroid spectral type the observed asteroid is, and if the asteroid taxonomy is somehow varying over the surface, so if there is a change in composition. And we can also map actually modal abundances of silicate minerals. So that's example here, the data products. This is what we expect to see. We have a Blender generated picture of or hyperspectral data cube of the asteroid, and we simulate also all the instrument noise, so it's how it would be seen by aspect. We also vary the spectrum based on the real spectrum observed by telescopes of the Didymos asteroid, and we apply to each pixel at a different illumination geometry. This is 30-degree phase angle, and then we run our algorithms on that. And here you can see how is the S-type asteroid spectral score. It's very similar to what is it observed in the asteroid spectra with ground telescopes, and here are calculated mineral abundances. We have a uniform composition, so there is also minimum variation. The variation is mainly because there are boulders and they can cast shadows or change in local illumination geometry, so that produce a bit this noise pattern. So this is also ready, and then we must prepare for the instrument operation. And the challenge here is that we will not have direct radio link with the satellite. We will only have some communication windows through the inter-satellite link between Hera and CubeSat. And the CubeSat will have to take care of itself for a period of 1 or 2 days. So all maneuvers, all operations of the satellite bus and also collection of scientific data has to be preloaded as a 2-day sequence. And in case of our aspect, we must power on the instrument, do some initial initialization commands, then do observations of asteroids, and we actually decided to repeat it several times, and then we have onboard algorithms to select the best image, and then download it to the Milani flight computer module, and then at the next occasion transfer it to ground and shut down aspect. So all this have to be automatized, and it's called so-called auto sequence. So this one was done last summer at the CubeSat provider, Tyvek International in Italy, and we thoroughly tested it, and now we are confident that actually all this initialization, acquisition, image selection, and storing of the images can be done fully autonomously without our manual control. So that's good. Last thing what we still need to do is actually to do a detailed observation plan. So we will have to have a 2-day plan how to do the observations and how to actually schedule them with respect to also the CubeSat maneuvers and, for example, charging batteries or basic functionality of the CubeSat. And on top of that, we also have to assure that if we observe the asteroid, it will stay in the field of view during the duration of the imaging sequence, which can take a couple of minutes. And we should also minimize the relative velocity to reduce any smear, especially in the very close operations at the end of the mission. So we will start with far-range operations from 10 kilometers with 2 meters per pixel resolution, close-range operations 5 kilometers, 1 meter per pixel, and then very close flybys, especially close to the DART spacecraft impact location to get a detailed picture. And here it starts to get complicated because the asteroid can leave field of view and you can have higher relative velocity. Each of the phase will take about 3-4 weeks, so we have about 3 months of operations planned. And we must schedule everything good. So this is ongoing together with CNES in France, who do the mission analysis and try to schedule the observations that we will get a global coverage within the 3 to 4 week duration of each phase. So how do we stand? Milani CubeSat will be deployed just in mid-January 2027. So 1 year from now, exactly 1 year from now. So we did process the calibration data. We prepared the ground processing pipeline. Okay, sorry. Where we apply the calibration and correction. We implemented also the data product calculation and preparation of the data product maps. So we are ready here. The auto sequence for the autonomous instrument operations are ready. And the detailed observation plan is still ongoing, and we hope to nail it down in spring or summer this year. So then it will be incorporated into the whole Hera operation schedule. So that's how we go. And maybe, if the time is right, next year on this meeting, we can have live stream of the deployment of Milani CubeSat and first images of aspect. Let's see what will happen. Thank you.
Thank you. Are there any questions? Are you going to do any kind of software updates to it while it's in flight?
So the CubeSat software is managed by Taiwan International, and they will still tune up and upload the auto sequences there. But first test was actually done in flight. So as I mentioned, we did the 2 acquisitions of the dark images. First of them was done in manual mode, so all these commands you were sending manually to acquire the dark images. The second test was done already with the auto sequence uploaded. So the second dark acquisition was done fully automatically. Concerning our CubeSat, we have a software there also on our own data processing unit, Q7 ARM computer running a Linux and custom apps. We have the option to flash a new version. We don't want to exercise this unless critically, because we don't want to disable the instrument. Even so, there are 2 versions which can be there, and you can boot from one or come back to the other one. So there is some safety factor, but so far we have some ideas which would help us, but unless really critical, we will not upload a new version.
Okay, thank you. Yeah, and I think we have to move to the next talk already, but thank you again. So next talk will be by Alessia Cremazzo. Is she here?
She's online.
Oh, online, okay.
You can open the Zoom.
Okay. So are you there? Can you hear us online? We currently can't hear you. Okay. So both of them are. I don't know, like, yeah, I wasn't aware of this. So is Sabrina Subki here also, or is it also online? Apparently not. Interesting. Okay, they're both online. Okay, yeah, that's new information. Yeah, could you share the screen at least while we figure out the voice? Or yeah, can you hear? Is it unmuted on our side? Okay, yeah, it seems to be working. Well, let's say if you are there, you can at least like write the message or something, or are you there at all? Okay, that's good. Yeah. So then we just can't hear you for some reason. And also, you can start sharing your screen. Yes. This is Alessia, the first one. Top one, yeah. Okay. Yeah. Okay, now you should have rights to share the screen online. Okay, you're in. And can you speak?
Now?
Yeah, it's working now.
Okay, now it's working. Before I didn't have the option, so
Yes,
sorry.
yeah, we
I'm going
fixed
to
it
share
just,
my
yeah.
screen.
Exactly. Yeah, now it's working. Thank you. Yeah, sorry for the delay.
Now you can see my screen.
Yes, it works well. Thank you.
Okay, so good afternoon, everyone. My name is Alessia Cremasco, and I'm a PhD student at Politecnico di Milano in Italy. I'm sorry I couldn't be there in person. I really enjoyed Finland during EPSC, and I hope I'll have the chance to come back one day. But thank you very much for the opportunity to present online. Today, I will talk about the science that can be performed through the Milani navigation camera or NavCam. As Thomas already mentioned, the Milani CubeSat is expected to be released from ERA in approximately 1 year. And Milani follows a very challenging mission profile. Do you see my second slide or still the title? Okay. And The navigation camera is based on the tieback star tracker technology, and its primary role is navigation. The NavCam will acquire optical images of Didymos and Dimorphos that are used for trajectory reconstruction, attitude determination, and to support the attitude autonomous pointing mode of Milani's DCS. In addition, the NavCam is a key element for the technological objective of Milani, and which is the demonstration of autonomous CubeSat navigation in deep space. At the same time, these images have a high scientific value because they can provide information on the global properties, surface characteristics, and dynamics of both asteroids. In the slide, you can see the NavCam and its integration into Milani's optical deck together with Aspect. The NavCam consists of an optical head, the detector, and a baffle. The optical head is composed of 3 lenses. The detector is a CMOS sensor equipped with an RGB Bayer filter, which allows us to obtain color information for scientific analysis. These RGB images of the NavCam can be directly compared with those acquired by Luke RGB camera on board the Licia Cube immediately after the DART impact. And also, NavCam images complement the spectral ranges of other instruments on board Milani and Hera, such as Aspect. And moreover, NavCam images provides different observation geometries with respect to Hera alone. And this slide summarizes the technical characteristics of the NavCam. The total field of view is roughly 20 by 15 degrees, and the detector has 2048 by 1536 square pixel with a pixel pitch of 2.2 microns. And this results in a ground sampling distance of 1.7 meters at 10 kilometers distance and 8 centimeter per pixel at 500 meter. And the optical head is designed to operate at distances between 30 kilometers and 200 meters, which are compatible with the observing ranges during the mission. The camera operates in the visible range between 400 and 700 nanometers, and although the detector is in principle sensitive to higher wavelengths, the signal-to-noise ratio drops significantly above 700 nanometers, and for this reason an optical coating was added to filter out the near-infrared light and reduce the noise. And on the right, you can see the quantum efficiency of the detector and the final camera response curves for the RGB channels after the radiometric calibration. And okay, in this slide, you can see an extract of the science traceability matrix for the NavCam and the potential of the NavCam to contribute to the main scientific objectives of Milani. Starting from the Milani high-level scientific goals, we identified the science objectives and the NavCam measurement requirements needed to achieve them. The first goal is determination of the global properties of Didymos and Dimorphos, and NavCam images can support shape modeling and rotation pole estimation. The second goal is surface characterization, focused on phase curve, spectral property measurements, and morphology. The third goal is the identification of the local shock effects on Dimorphos caused by the DART impact, and the NavCam images can help detect surface morphology changes, including the possible presence of an impact crater, and can also contribute to spectral investigation. Finally, NavCam support the gravity field determination through optical navigation and the observation of ejecta dynamics and by monitoring the landing of the other cubes at Juventus. Okay, and one of the main scientific objectives of Milani is to provide a global shape model of both Didymos and Dimorphos. And on the figure, you can see the shape model of Didymos thanks to the images acquired by the Draco camera on DART. And for the Dimorphos, the shape is very important to assess the effectiveness of the kinetic impact. And to achieve the shape modeling of the asteroids, NAVCAM will acquire images under different illumination and viewing conditions, optimized for shape reconstruction. And here in Milano, we'll be observing the asteroids with different geometries and illumination conditions, and therefore NAVCAM observation will provide both an independent estimates of the global properties and shapes of the asteroids, to be compared and validated with the estimates from other instruments, and also a way to refine and complement the observations from ERA asteroid framing camera. Then the surface science investigations can be divided into geomorphological and spectral studies. From a geomorphological point of view, NAVCAM will provide a global surface map of both asteroids. And one key product is the surface slope map, which then combined with gravity and rotation models allows us to derive a geopotential slope map. And the geopotential slope measures the angle between the surface normal and the local acceleration vector. And you can see in the figure the current geometrical slope and geopotential slope of Didymos. Additional geomorphological investigations include the analysis of boulders, distributions, the morphology of surface materials, and the identification of features such as craters, thermal cracks, and ridges. And NAVCAM can also contribute to spectral investigations, despite being a navigation camera, and mapping the spatial distribution of shocked or freshly exposed material helps us to understand the consequences of the dart impact. And also spectral variations can indicate the space weathering processes. And to evaluate NAVCAM's capabilities to detect surface heterogeneity and composition, we simulated its response using Bennu as a test case, and spectral data from an instrument on OSIRIS-REx were converted into synthetic RGB measurements, as they would be observed by the NAVCAM. And these simulated measurements were then clustered using a key-means algorithm. And the resulting clusters are shown in the figure and show a good agreement with the spectroscopic mapping of previous results. And this demonstrates that the NAVCAM has the potential to detect surface heterogeneity on Didymos and Dimorphos. And to link the RGB measurements to the composition of the asteroids, we simulated the NAVCAM responses using laboratory spectra from the RELAB database. And a set of these spectra can be seen in the figures. And using the RGB sensor response curves, we simulated the NAVCAM RGB measurements related to this material. The bottom left figure shows that for shocked materials, changes in RGB ratios are small, in the order of 1%, and may be difficult to detect. But in contrast, space weathering effects produce a clear reddening of the spectra. And in the figure at the bottom center, you can see that the red to blue ratio can increase by more than 10%. Due to space weathering, and therefore the RGB camera is likely capable of observing surface weathering processes by measuring the distribution of the RGB ratios across the surface. And therefore, NAVCAM data can be combined with spectral instruments like aspects to improve the overall surface characterization. The NAVCAM can also support gravity field determination, and the University of Bologna leads the gravity field determination through the radio science experiment, but NAVCAM images can support the experiment by providing different observation geometries compared to ERA. And also NAVCAM can track small particles and boulders orbiting the asteroids. And this technique of observing particles around the asteroids was successfully used at Bennu to refine gravity models to higher degrees. And in the figure, you can see some qualitative figure of the detectability of particles and ejecta around the binary asteroid systems, depending on the size and the distance and the phase angles. And additionally, NAVCAM will observe Juventus landing and therefore can provide constraints on local gravity near Dimorphos. And this slide introduces the Autonomous Optical Navigation Experiment, or AuTOP-NAV, and the goal is to validate Milani's onboard autonomous navigation capabilities near the Didymos system as a technology demonstration. A dedicated Navigation Experiment Operation Center, NIOC, located at Politecnico di Milano, will collect and analyze GNC data. And onboard navigation solution, which is centroid-based, will be compared with ground-based reference solution based on landmark navigation. And the navigation error is the difference between the solution computed on board, so centroid-based navigation, with respect to the ground solution, and this will be the main performance metric of the experiment. And to conclude, the Milani navigation cameras operates in the visible range between 400 and 700 nanometers and provides RGB color images. Also, it was designed primarily as a navigation instrument and not for science. It enables a wide range of opportunistic science investigation. And NAVCAM data can complement other instruments on Milani and ERA in terms of wavelength coverage and observation geometry, contributing to the characterization of global asteroid properties, surface morphology and composition, and the assessment of the dark impact outcome. And finally, NAVCAM images are fundamental for the autonomous navigation technology demonstration. So a camera designed for navigation turns out to be a versatile instrument with significant scientific return. And yes, thank you for your attention. And if you are interested in knowing more, here's my email.
Okay, thank you.
Thank you.
Hopefully hear the clapping over the microphone and know if it worked.
I cannot hear, but thank you.
Okay. Yeah, so do we have any questions from the audience? Okay, it seems that there are no questions at the moment, but thank you for your presentation. It was really good. And yeah, since we had technical difficulties, I think it's best we move on to next talk. But yeah, thank you again for your talk. Okay, so next one also is going to be online. She was already there before. Yeah, allowed to talk, I think you have to. And okay, so Sabrina, you should be able to share now. And hello?
Good afternoon. Can
Great,
you
yeah.
hear me?
Yes, we can hear you, yes, yeah.
Okay, so let me share the screen. So you should be able to see my presentation, correct?
Yes. We see your screen, yes. Yeah,
Okay.
now it's correct. Yeah. Thank you.
Okay. So good afternoon, everyone. I'm Sabrina Sughi, PhD student from Politecnico di Milano. Unfortunately, I couldn't make it there in person, but thank you for the opportunity. And I'm glad to present you today the ESA Lumio mission. So Lumio is a CubeSat mission led by Politecnico di Milano that is planned to be launched in 2028 and will operationally fly for 1 year in a quasi-halo orbit around the Earth-Moon Lagrangian point L2 in order to detect flashes from meteoroid impacting the Moon on the far side. It has been a long journey for Lumio since 2017 when he won the award of Luce ESA Call, and now we are approaching the kickoff of Phase C the next month. So the main objective of the mission are, on the science point of view, to refine the lunar meteoroid environment and so characterize the meteoroid flux at the moon and the related spectrum of energy. While technologically speaking, the mission serve to demonstrate some CubeSat innovative technologies such as the miniaturized propulsion system, the performance of an autonomous navigation experiment, and the use of CubeSat in the lunar environment. So regarding the science objective, what we are going to measure is and detect is the radiation emission after a meteoroid impact. So the fraction of the kinetic energy of the meteoroid that doesn't go into crater formation or particle ejection. So the detection will tell us the number of impact that we have on the moon and information on the energy distribution of the impacts. So nowadays the lunar impact flashes or LIF have been observed from Earth by different missions such as Nedeota or Midas. But we are going to be the first mission to observe this impact from space. The science objective of the mission will be the assessment of the meteoroid flux at the moon and the energy distribution. And what we aim to do is to fill up a detection gap that nowadays we have. So there are detection for low range of energy, as you can see, for high range of energy, but there is a gap between 10 to the minus 4 to 10 to the minus 1 kiloton of TNT equivalent. And so, because there are no physical reason for this gap, we think that with Lumio we will able to cover this range. Regarding the spacecraft, the CubeSat is a 12U CubeSat, specifically designed for the mission by Argotech. And while regarding the payload, and so how we are going to do the measurement, is we have the LumioCam, so an optical sensor that has a 2-channel, so the measurement will be done in visible and in near infrared. This double measurement is to validate the impact, the event, so not to have a false detection, and also to retrieve information on the temperature of the impact by the difference in color. So about the sensor, there is still ongoing trade-off between a CCD and a CMOS sensor, but most likely we are going to go for the second one. Here you have the mission profile. So we have the launch, the commissioning, a long transfer to minimize the energy consumption, and then 1 year of operational phase at least. The operative phase is divided in the science cycle and navigation and engineering cycle. In the science cycle, there will be the actual detection of the impact on the shadowed part of the moon. Part of the disk. So we need the moon to be, the disk to be shadowed at least at the 50%, this to avoid excessive saturation of the frame and to allow enough time for the other part of the operative phase, so the engineering and navigation, during which there will be the downlink of the data, some CubeSat related activity, such as the reaction of the reaction wheels, and the performance of the autonomous navigation experiment. So here you see the quasi-halo orbit, a large orbit around the L2 point here in the Earth-Moon rotative reference frame. So as you can see, the orbit, we will always have the full coverage of the far side of the moon, and thanks to the optics, we have the full disk always in the field of view. The large orbit allows us to have the Earth always inside, and this will also allow us to slightly observe the poles. So compared to Earth-based measurements that are limited by night observation and the presence of the atmosphere of the Earth shine, Lumio will have a continuous detection and cover during the science, or when the moon is shadowed enough, and unbiased detection, so not spoiled by the atmosphere or the earthshine for 2 weeks, then 2 weeks of engineering and navigation, and so on for at least 1 year of operational phase. While as an end of life, now we plan to crash into the moon, and of course avoiding a protected side, as you can see. Lumio has also a science team that is led by Politecnico di Milano. Here is divided in working groups, 4 working groups, one for meteoroid, one for surface and impact, one regarding lunar and environment engineering, and one about citizen science and outreach. So each of these working group is researching on a different aspect of the mission, while we have also a group in charge of the Science Operations Center, so the center that will deal with the data once the mission is operative. Nowadays, we have an overall of 65 people actually working on the science team, all led, as I said, here at Politecnico. Some of the ongoing activity by the science are related to what Lumio will potentially observe and what will not possible to Lumio to observe due to morphology or illumination limitation. So we are getting prepared to correct the meteorite flux that we are going to detect and measure. There are also some studies for machine learning use to retrieve the meteoroid stream association with the impacts, and studies on the possible algorithm to use to localize the impacts, because due to the high amount of data, we will not download the full frame per impact, but just a cropped area around any detected impact. So classical limb fitting and feature recognition algorithms will not be possible, and so we are thinking about alternatives way to localize the impact. And of course, meters to compute the meteoroid and to relate this to the meteoroid flux at Earth. Another important activity that we are carrying is the production of synthetic images, so synthetic data that mimics what we will actually observe with Lumio. So we have an internal tool, Abram, that is a realistic render. And with this picture, we want to train the localization algorithms, the navigation algorithms, and also get ready with the scientists to get the most out of the scientific outcome of the mission. Lumio is part of a consortium, so that involves different national agencies with a major contribution by the Italian Space Agency. Everything is coordinated by ESA, while the prime contractor and the mission manager is here at Politecnico di Milano, with few companies involved in the mission. So with this, I thank you all for the attention, and I don't know if we have time for questions, but in case, feel free to reach out to me at my email here. Thank you again for the attention.
Thank you. Do we have any questions from the audience? There is one question.
Do you see there being any potential use for an event-based camera in this mission?
I'm sorry, for what?
For an event-based camera.
What do you mean with event based?
Yeah, event camera, I mean.
I'm sorry, I can't hear. Advanced
event.
So the camera will keep detecting. So there will be an algorithm that once that it will keep shooting image, let's say, and after and delete them when the algorithm is triggered. So when there is an event detect, those frames will be saved, like cropped area. And I don't know if this answers your question or.
Yeah, I think it actually does in a way.
Okay. So yeah, there will be a continuous detection, and so capturing image, delete, and capture. Yeah.
There is another question.
Yeah, just a quick one, Tomáš Kohout. How many events you expect to record a day, a month, or a year?
So at per hour, like 2-3 events per hour. Then of course we will have a peak moments during the meteor shower event. I believe that now we are doing calculation for the data for 60,000 events per year. But roughly,
so
yeah, those
quite
are
a
roughly
lot.
estimation.
Thank you.
Thank you.
Okay, any more questions? Or yeah, seems to be the so. So thank you again. And
thank you again.
Yeah. Okay, so there will be a break now, and the next session will start in 15:35 with Tomáš.
Yeah, 15:35, last block. Welcome. 15-minute break. Back to the session, last block. We will have some astronomy observations and so on, and the first talk is by Anne Virki about polarimetric radar backscatter roughness metrics of the lunar highlands and Maria, so the lunar observations. Please. 12 minutes for talk, 3 minutes for questions, 15-minute block time.
All right, hello everybody. So I'm going to give a talk on some preliminary work that we are doing on polarimetric radar backscatter roughness metrics on the moon. So this is actually a paper in preparation led by Edgar Rivera Valentin. But I'm going to give you some highlights of the study that we are doing. All right, so some context. There is some renewed interest now in the manned missions to the moon. For example, the Artemis program, you're probably familiar with, but also China has some plans to send people to the moon again. And this, for example, the rock abundance is relevant for this kind of like landing site evaluation. Of course, it also can have other implications to just general crater characterization that can have other scientific interest. And radar polarimetry has been used for several decades to assess surface roughness for planetary bodies, but it has been a little bit of a hand-wavy measure. So this kind of like a first order, low values for smooth-ish, high values for very rough. So the idea is to give a little bit better quantification for these metrics. Also, linear polarization features in these lunar polarimetric images have been a bit of a topic of debate. They are partially known to be artifacts, but there could be also some real features in there. And we are going to be determining these specific polarimetric values as a function of rock abundance. Okay, so all the data we use is based on lunar reconnaissance orbiters, different instruments. So the mini radio frequency instrument is a polarimetric synthetic aperture radar. And then we also use this diviner lunar radiometer experiment. So I'm going to use short DLRE for diviner, which can infer the meter scale rock abundance from thermal measurements. And mini RF used to transmit this kind of like 13-ish centimeter radar waves. And it's kind of fully polarimetric, so it transmits in essentially effectively in circular polarization at a 50-degree incidence angle compared to the surface normal. And then it receives the signal echo power into orthogonal linear polarization, H and V, but also the phase difference between them, so you can derive also the circular polarization. And this information then can be used to get all the 4 Stokes elements, which describe the full polarimetric states of the echo. So here you can see as equations the 4 elements, I, Q, U, and V, or in some cases it's written as S1, 2, 3, and 4. So the interpretation for these elements is essentially 2 linear polarization components and their orientation, or like the handedness of the circular polarization. And here you can see example of the data of these 4 channels for Giordano Bruno crater, plus the incidence angles and the rock abundance that have been measured with the diviner. And well, you can't see very much in these maps, but actually if you normalize the 3 elements with the S1 component and use a logarithmic scale for the S1, then you can see a little bit more features there. So again, the illuminating signal is circularly polarized, and this is radar. So if you're used to optical methods, please note that here the circular polarized channel will be essentially the strongest one, whereas in like optical measurements, you're typically looking at unpolarized sunlight reflecting from the surface. And here you can see the linear polarization artifacts that I mentioned. So there are these kind of actually quite striking bands which are visible in this S2 data. And they are quite common actually near bright craters. And they are partially caused by this kind of glitch in the signal compression algorithm. So when the radar is kind of passing past this kind of like a very strongly reflecting crater, something in the algorithm glitches in this specific polarization, and it's gonna create this kind of like a few percent kind of error in this specific channel. But the S4 is fine, and the excuse me. So the technical staff is telling me that the band should be excluded from any polarimetric analysis. Of course, I'm not going to do that. I'm just going to treat them with a little bit more caution. So here, for example, we are doing this kind of visualization of the different polarimetric channels using these kind of like color channels. So in the red channel, you have the linear polarization, the S2, essentially. So it's just been scaled a bit to be between 0 and 1 instead of -1 and +1. So at 0.5, you have a kind of the 0 level for it. And then in the blue channel, the same thing for the circular polarized channel. And then in the green channel, you have like a combination, which is related to the full degree of polarization. So you can see essentially the relative changes around the crater for these different channels. And again, you can see the artifacts as these kind of bands around the crater. It is kind of like a bit cyan color maybe, like a little bit bluish. You can see in the lines on the right that the linear polarization component kind of goes actually quite a lot to the negative side and then bounces back to the positive side. And this is specifically the values on the line shown by the arrow, like the little black arrow there for row 200. It actually may have changed a little bit, but it should be for row 280 and not 350. All right, so if we do exclude the artifact bands and look at only the S2 and S4 channels, normalized with the S1, you can see that there is actually quite clear trend as a function of incidence angles, which are the angle beams, and the rock abundance. So technically you could use both of these to infer rock abundance if you know the incidence angles. Also, often we use these different circular polarization elements, opposite circular and same circular compared to the transmitted signal. And you can see, again, here you can technically use both of these as unambiguous measures of the rock abundance. Whereas the CPR, the circular polarization ratio, which is the most commonly used measure for interpretation of roughness or rock abundance, could be, you can see it's actually not an unambiguous measure. But at the high rock abundance, you actually might get this kind of decrease of these curves. Okay, so we're doing some modeling because from Diviner we only get meter scale information, whereas for radar we are looking essentially at decimeter scale information. So to match the meter scale information to the actual size distributions, we have to do modeling. So in this case, we are simulating these rocky particles using advanced discrete dipole approximation, using realistic refractive indices and particle shapes, because we know that the shape also matters a lot in polarimetric measurements. And we are using, in this case, size parameters only up to 8-ish, which for these like decimeter waves, the 13 centimeter waves is about 32 centimeter particles. So for this kind of preliminary look into this. And also the incidence angles are ranging for single scattering case up to 60 degrees, but we are also doing these multiple scattering cases where we have several particles on the surface, and we're looking at also like the multiple scattering effects. And in this case, we have the incidence angles go up to 85. If you're not familiar with size parameter, it's defined down here. Okay, so what we're seeing, essentially, so these are the Stokes parameters, I, Q, U, and V, normalized by I. So essentially for the I component, the intensity, you can't necessarily like scale it directly to the observations, but you can see the relative changes as a function of the incidence angle. So for example, you can see this interesting like increase again, like back in the higher incidence. For Q, you can clearly see that it goes to non-zero values. If you have these particles in free space as a cloud, you would see just 0. But in this case, if you have the higher incidence, you can clearly see that it should have values of like -1. I mean, minus 0.1. And again, same for the V component, you can see like a clear function of the incidence angle. And the number of realizations is still quite low, so we need more of these, especially these multi-particle cases, and also maybe larger particles, which I'll show more on the next slide. So here we have, again, the polarization elements for the circular polarization as a function of the rock abundance. So the panels on the right, as I showed earlier, are the OC, SC, and CPR, which are, again, here. So these black lines are modeled. So here you have just a single particle cases, and these are kind of weighted averages over a size distribution that follows a power law, but it has the maximum size of the particles is increasing here on the x-axis. Thanks. So you can see the increase as a function of the rock abundance is here at the function of the maximum particle size. And the different line styles are the different power law size distribution, the power law indices, because we don't know exactly what is the correct power law index. But you can also see it doesn't necessarily matter that much for some of these, but then for some of them it matters more. And yes, you can see the increase. You can see this kind of plateauing, but you can't see the decrease, for example, in the CPR, which could be because we don't go to as high particle sizes in this case as there is, or we are not including the volume scattering component in this case. So conclusions, we are determining specific polarimetric values as a function of rock abundance because this rigorous quantification helps interpretation. This can be for landing site evaluation or more generally for crater objective characterization. And we can find that these circular polarization components increase directly proportional to the meter scale rock abundance. And using just these surface particles alone, we can simulate these functions, although adding the volume scattering would improve the results further. And these striking linear polarization features, which are visible around many craters, they are known to be partially artifacts, but to what extent? And we already know from the graphs that the linear polarization does have a clear dependence also on the rock abundance when the artifacts are excluded from sampling. All right, that's it.
Okay, thank you. And we have time for one quick question, if any, before we move to other talk. Quick. You don't ask quick, so I say you quick. Okay. 20-second question, 20-second reply.
No, I'm fine.
Yeah, and you consider particles embedded partially to substrate, right?
You know that other can't do that.
Yeah, I'm just wondering what is the size of substrate in terms of sizes of particles, boulders?
Yeah, so this doesn't actually include the surface. It includes only the particles, because if you come from like an incidence angle that's relatively high, we assume that the surface itself doesn't contribute as much as the particles do.
Okay.
So it doesn't matter as much.
Okay. Okay.
Yeah.
Thank you.
Yeah, this is not, phase angle / scarring angle.
Okay, thank you. The next presentation, Silver Muru, if I'm correct, lunar rover wheels. Please, floor is yours.
So good afternoon. A full house at this time, this is good. So I'm Silver, I'm with the Kupkulger team and also a PhD student in Tartu Observatory studying digital twins of lunar rovers. And one of the topics which is one of the fundamentals for digital twins is thermomechanics of the wheels. So thermomechanics is the field that studies mechanical interaction between the wheel and the formable soil. So formable soil is more difficult than hard surfaces. And the goal is to have better prediction and increase performance of the wheels. And as you know, in lunar cases, performance for us is very important because we want to get from every kilowatt of energy, kilowatt-hour of energy, we want the best performance because we have limited in it, and the wheels or the movement takes anyhow in the energy budget one of the biggest parts. So even like a small percentage or 1 or 2% of efficiency increase is a massive increase or win for us. And this field is several decades long or old. It started in the 1960s from a Polish engineer. And the concept quite arbitrarily can be divided into two. So we have the classical thermomechanics or approach, and the second one is machine learning. For the classical, several people throughout the years have developed quite good tools and techniques how to determine the wheel interaction with the soil. But in the last, let's say, 5 years, more and more papers have come out with using machine learning to find new ways how to find better ways for the wheels. For example, there's a chance that we can use the wheels or the axles to determine the soil on the go, on the field, which for us maybe it's not that relevant, but what it is, for example, is the last one, having an adaptive mobility control. So instead of telling the rover to go from point A to point B with constant RPM, we can, in the software, determine what's the RPM in certain situations should be, and we can, that's why, have a better performance. And the motivation for this work is in this picture. Looks like a Christmas tree for engineers, but actually what you see in this picture is waste. Waste of material, waste of time, waste of engineering potential. So what we don't want to do is build more wheels to test them, like is this the best one? Instead we want to do it in software, and then if we have determined that this is the best wheel for this case, then we can go and manufacture it instead of building more than 20 different wheels and test them out in different conditions. And like most projects, and including Kupkulger, have humble beginnings. So with thermomechanics in Tartu Observatory, we have built 2 different test benches, the round one and yellow one. For the round one, I had a bachelor student who was working on different wheel designs. And this wheel, the round one, for example, we had a test where the wheel could drive 24 hours in a circle, managed to travel around 10 kilometers. So we know for that, like, we can test motors even with this one. We can we have a motor that has traveled more than 100 kilometers in observatory. And on the right is a linear test bench. The first version, quite rough one for the beginning, but the new improved version is now in the use. And even the simple test bench with the round one gave us few good insights. For example, the wheel attachment. I'm pretty sure this wheel was attached to this motor. When I tried to pull it off, it didn't come off, but after 5 kilometers or 5 hours of driving with constant axial force and some vibration, the wheel came off. And this rock here was 2 times bigger than it was before, until it came to an angle where the wheel wasn't able to get over it and then find a good place to hide itself. This is also a video of the same effect, that both wheels worked really well on on the surface. It traveled worse, there was no slippage, but when it hit the rock, then it became a bulldozer. For the linear test bench, this is the first version made with aluminium pipes laying around. It wasn't the best test bench, and wasn't also even the approach wasn't correct. My initial idea, like what we should measure, wasn't good. You can see if the force meter is here, measuring force in a vertical direction using a spring, but it was completely wrong. There was no actual good information in it. But it shows that first initial idea isn't always the best one. So the current, so the current wheel test bench has much better rails, so there's no misalignment in that one. And here you can see the force meter is in the new position and even new axis, that we're now able to measure the force that acting upon the wheel. Here's some pictures, but we can go to this one. You can see the plate where the force meter is pushed upon. But this will probably show the best how the setup is done. So we have 3 linear movements and 3 axial. So everything moves in this blue line, or all of this, everything is in the middle, is driven by this big motor at the back. This represents pretty much the rover movement back and forth. So we can make the rover move faster and slower, depending do we want to go uphill and downhill. So the second axis is up and down, so vertical. So everything which is green and below this line can move freely up and down in a vertical direction. And this movement can be measured using a linear encoder. And the third degree of freedom comes from this red part, and the wheel and motor itself can be freely moved back and forth, and then this presses upon a force meter. The sensors that we're using are these. I'm very pleased with the linear encoder. When you look at the resolution, I had to double check if the number is correct, but it should be. It's 0.02 micrometers, which I didn't know it can go that low, but I'm using this capability, like really good accuracy. But on the force meter, the initial one that we bought is a bit maybe overkill. It can measure 200 newtons, but we don't see those kind of forces, and the resolution maybe is not the best, so we have to maybe switch to this different sensor in the future. There's also initial data from these 2 sensors. Unfortunately, didn't have that much time to do the test run, so the new bench is quite new. So maybe next year I can present more data and conclusions from this test bench. In the pipeline, there's also a few ideas. One is using the axles itself as the test in the unit, or unit in the test. So we can maybe in the future use the sensors inside this axle as well, determine what the wheel is doing and how to increase the performance. And also there's a need for something to level out the ground or gravel in between tests. So one way is using vibrations. So every time after the test is done, the wheel makes some bumps in the gravel, and then we need to level it out somehow. So there's a need for this as well. Luckily, we have also a lunar analog site in sight, so we can travel from the tests to the actual rover is quite fast. We don't have to go to somewhere to test the new algorithms or do new approaches. And also everything should be come down also to the digital twin part, that we will have a lunar rover that behaves in a simulator as accurately as possible on the ground, and hopefully in the future on the moon as well, so we can build a better rover and even maybe skip the part of building like a physical twin of a second rover, which is usually done on bigger missions and in the past. And this is for my part, and my Finnish friends, our slogan in Finnish. Thank you so much. I hope I was on time.
Thank you. We have time for questions.
Thank you for the presentation. Since you've shown in the beginning that there's many different types of wheels that you can produce and test, has there been also the idea or work in the direction of making wheels adaptive for different grounds? I don't know if that's even possible, but just seeing that that there seems to be different wheels for different grounds apparently. So
for the wheel to be like it depends if it takes energy when traveling or not. If it takes too much energy, we can't use it because we have a really limited energy budget on the moon. But if it's possible, and then for the having the wheel to be soft, we also, I guess we don't need it that much because we have the axles, we have the that has take the roughness out. Which for if you have four wheels, then you need something that observes the movement. But for the adaptive ones, maybe if you have ideas, then that's good.
Not directly, but I guess since they're so, let's say, soft in that sense, they're already a bit adaptive to the ground anyway in that sense.
Well, the problem with wheels is that wheels that go well, like in one direction forward, don't necessarily have good turning capabilities, which is also one conclusion from several tests.
Right. Thanks.
What about the wheel material? Is it made from standard aluminium, or have you considered some other materials which are more durable on moon surface?
Well, durability of aluminium hasn't been a problem. The same motors that ran for 24 hours, also in aluminium, they had a more roughness on it, the surface, but nothing break. And aluminium is somewhere in the sweet spot of the weight and the strength. Maybe beryllium is better, but beryllium has some bad properties as well, being toxic. But beryllium in the strength and weight-wise is better than aluminium, maybe. But ideally, also you want to keep the aluminium from one material, so you don't want to have screws inside the wheel. Inside the wheel.
Yeah. Okay. Yeah. Thank you.
Thank you. The first Chinese lunar rover had some problems that it was sinking into the regolith and did not really work. What did they get wrong, in your opinion, and how would you prevent this issue?
Probably lack of data.
I think they had too small wheels. Somebody told me that they stole the NASA rover Sojourner design, and there is a stronger soil on Mars than on the moon, and that's why it was sinking. So you have also quite narrow wheels, actually. Is it enough to carry the mass of the rover?
Right now it hasn't been a problem, but this is something that will come in the future.
Okay. Thank you. Thank you. So yes, next talk, Quasi Simon Islam about useless, or how you pronounce your project. So explain us what is it about. Welcome.
Yes, I'm just waiting for the slides to come up. Hello, everyone.
Ulysses.
Yes, Ulysses. The first part is going to be all about the name, so thank you for bringing it up. My name is Qazi Simon Islam. I'm a PhD student at Tartu Observatory. Been working on this for most of my PhD, so hopefully you'll get a good context of what Ulysses is and what we're going to work with. But I don't know where the clicker is, Silver. Okay. Thank you. But before we start, can I get a show of hands to see, like, have you heard the name Ulysses in Tartu? Okay, one. Okay, can I get a show of hands of people who've been at our booth of Tartu Observatory? It's the same hands. Okay, good. Now we're a bit warmed up because we got some physical exercise, so we're a bit more awake. Let's go. So what exactly is Ulysses? 4 years ago, me and a few other PhD students at Tartu Observatory and other colleagues were working on a simulator tool, and we needed a name. Me and particularly Hans Thras, one of our colleagues, we were quite inspired by the story of Odysseus, and we really wanted to fit the name Ulysses to our simulator. So we came up with this really convoluted acronym for it. And if you're thinking that this is one of the cases where scientists are fitting an acronym to find a good name, you're absolutely right. But what Ulysses actually is developing large-scale simulations using actual space data. So here, for example, is a lunar DEM from the Apollo 16 landing site, and we use modern game engines like Unreal Engine 5 to harness their capabilities to be able to simulate them as realistically as possible and make them usable for science. That's the whole goal of Ulysses. And while we're here, I never really liked this really long acronym, so for now, Ulysses will be Unreal Engine layered planetary surface simulator for exploration suite. Still convoluted, but a little better. How it started was in 2022, we had a project with the European Space Agency and Milram Robotics where we had to develop a lunar mobility planning tool. We had developed such a tool where you could mark down different points on the lunar surface and our software would spit out a planned path. But we had a very practical problem of how could we even validate whether our software is doing the right thing, especially because our software had to take into account dynamic cost of shadows as well as static costs. So we decided to put the same map we use for planning into Unreal Engine at that time. We knew very little about Unreal Engine coding, so everything was hacked together. But by the end of the project, we had a simple mission validation, which actually was really appreciated by ESA because you get not only qualitative validation, but also good understanding of how to tune your path planning software. So we had a good feedback back and forth between the two. Few years down the line, this is the overall framework of Ulysses now. So we have actually been continuing to research many different parts of how to reuse the same framework to do different applications. So we have been working on strategic mission planner, basically making the whole user interface in the same environment. We've been using the tools to generate orbital data, so you can mock up how satellites are flying over the moon and then use that as a prediction of how your satellite should be angling its cameras, etc. We've been using it as a synthetic data generator for surface level operations. And we've been, as Silver discussed, looking into how to develop a proper rover digital twin, because that's where the future is, so that you lower the cost of your work by simulating everything in software rather than building it and testing it outside everywhere. One thing that is quite new is we have also been started looking into VR applications, because we see that there is a good opportunity here to reuse all of these same tools to develop like training or educational capabilities through virtual reality. Today I'm going to talk about these three modules particularly because I wanted to, but Also because the other two, I think we've talked about quite a lot, and there isn't anything significantly new, but there's been some really good advancements through project-driven capabilities. And I think we all know that in space research, everything is driven by projects. So if you have a project, you have good requirements, you have good understanding of what is needed, your development goes faster and faster and faster. So we have two ongoing projects that really support Ulysses. One is an ESA RPA with ProExpert RS, which is an Estonian company. And the other one is my own personal co-funded research, OSIP research, that I've been doing since last year. There are also other supporting projects that support other parts of the modules, but I'm not going to be covering those today. And of course, we have Kuupkulgur, which is kind of like the main star of Ulysses as well, because it started around the same time. And because we have a rover platform, it's a lot easier to do the rover digital twin stuff. But the concept is that we use Kuupkulgur as a study point of how to develop this rover digital twin, but the same tools can be applied to your rover or your systems that you want to integrate into our environments. So what is a digital twin after all? How do you go about developing one? We want to do it, we have some data, but how do we know how to simulate it well? Let's take the idea of the Lunar Analog Facility at Tartu Observatory, for instance. We want to, for the ProExpert project, we needed to develop a pipeline where we have similar synthetic data for what comes from the rover and its tests in the analog environment. So we had to take a map or develop a map for the Lunar Analog Facility. We did this with laser mapping of the environment. It's really cool. At Tartu Observatory, we have so many tools and people able to help us. The remote sensing department just said, oh, let's just go to the bunker and map it out with our cool tools. And by the end of it, we had a digital twin that we could import into Unreal Engine. This looks very simple and straightforward, left to right, but in practice it took months of cleaning up this LiDAR point cloud that we recorded and then meshify and then bring it into Unreal Engine. But by the end what we have is a digital twin which is quite similar to each other. This is a top-down picture. Can you tell which one is simulated, which one is real? Good, confusion is good. So the right one is simulated, the left one is actually from an overhead camera in our Lunar Analog Facility. And this is what we want. We want to blend this gap between simulation and reality and bring it as close as possible so that, same things, so that we could use the software to generate synthetic data that we can't easily get our hands on just with the rover. So with the rover, we can gather data with the sensors, etc. But with the simulation tools, we can not only get RGB frames and sensors that we can model, but we can also get depth frames, something that is not easy to get straight away unless you add more sensors onto your rover. And we can also get annotated ground truths. That's the real strength. You can do supervised learning through the synthetic data that we can generate. This is an example of the left, again, being the real rover driving around. On the right, you have the digital twin of our Kuupkulgur rover driving around in the lunar analog environment. And throughout the year, we've been doing this qualitatively, putting post-process volumes, looking how the shadows look, seeing how everything kind of lines up. We even put some texture on the walls because we have walls in our Lunar Analog Facility and they have some imperfections. So we've been trying to improve the visual fidelity of it. But at the same time, we've been thinking about how to actually record the data, because if you think about it, if you don't have a really good computer, your game stutters. So how do you deal with that problem? You don't want your synthetic data to come in at variable frame rates, right? Because that's not a real representation of what your rover is capable of doing. So what we actually do is utilize Unreal Engine's separation of runtime operations, where we set up our level, we set up our rover digital twin, we drive the rover around and capture the trajectory in which it is driving. So if I do a figure eight, a circle, drive whatever. At this time, it has already captured the ground truth trajectory that the rover has driven. Then we load whatever camera recording setup that you need and load it into what is called a sequencer in Unreal Engine. This allows us to then configure different render capabilities. So you can also actually do the recording in lower visual fidelity if your computer can't handle it, and then press a button and render out the data using a different subsystem that does it independent of runtime. That means that if you want 4,000 frames, you're going to get 4,000 frames regardless of whether your computer is able to handle the memory usage or not. This was extremely efficient, and this is an example of the user interface that we made. Once again, we're engineers and not graphics designers, so please don't crucify me for all the fonts that we've used, but the idea is exactly like I was discussing. Right now, we're driving around, capturing the trajectory that the rover is driving. It's recording how it's moving around in its environment. All of this is getting logged, including the sensor data that I mentioned. We've modeled IMUs as well as the encoders, the exact same sensors that Kupkulgur has. Then I select the render configuration, what I actually want to render out. Rocks, terrain, those are all being mapped as binary maps. And then in the subsystem, oh, there was a bug. I didn't select the run that I wanted to render anyway. And then you can see that all of this is getting rendered out in runtime. And this independent of the runtime. And how fast this rendering happens is totally dependent on the computing hardware that you use. This particular video was recorded on my laptop, so it is definitely possible to run it off a good gaming laptop if you want. And the way we've set up the software, you go into the folder and everything is then ordered nicely, ready for use. Okay, this was not ordered nicely. But this is the point. Through this project that we've been doing with ProExpert and the ESA OSIP, the goal has been to make the user interfaces a lot more convenient so that you don't need to know the underlying code or how things work. You can just get things running. I want to quickly wait to, yes. So this is where everything gets dumped. So frames, depth images, and masks of individual objects, etc. On the larger scale, as I said, we can load lunar DEMS and then lighting conditions as well as add procedurally generated assets. This is something that I've talked about before here as well as at our booths. But for larger cases, what we decided is that rather than cumbersomely driving around a rover for hundreds of kilometers, you can actually just put down different points and then basically use the same rendering outside of runtime as your render engine. For synthetic data generation, why this is important is once you've actually identified where you want to drive, you can actually mock up different camera configurations. So here is an example of using New Scene's camera configuration, which has 6 cameras, and we can actually render out thousands of images all together without actually having to do it individually, and they're infinitely repeatable if you want it to be. What's next is going from qualitative to quantitative. So that's something that we're currently missing, and that's what we want to look into this year. One thing that I wanted to quickly give an example of is I've started looking into seeing the differences in how shading works in Unreal Engine, and by implementing something more scientific like Takka, and figuring out how far off are we scientifically from the rendered images that we get out of it, and how much can we rely on them. Also looking into implementing other sources of data such as albedo maps, roughness maps to improve our visual fidelity of the actual lunar simulations at the end. Virtual reality capabilities, I think it's best if you come to our booth and try it out, but the point is that the same data, the map that you're seeing here in this video is actually generated from this Apollo 16 map that I showed at the start. So all of this is recreated using actual lunar data. But yes, it's really fun. I would really highly recommend you guys to come, but there is a lot of application domains that are very useful, like HRI simulations or education and even astronaut training. Finally, what's next is actually completing the development cycles of the current projects. That raises our TRLs. And looking into additional application domains like lunar landing. It's been something that ESA themselves have requested me during my OSIP to look into, but also why we restricted to the moon. Ulysses is supposed to, it has 4 different maps here, so Moon, Venus, Mars, and Earth. We can now actually start simulating something like drone flybys because now we have the tools that we just need to transfer from one map to another domain. With that, I want to quickly say that these are the main people who have worked really, really hard with me on Ulysses over nights and over the last few years. But all of this is only possible because of the rest of them who will sit and very patiently listen to me complain about why Unreal Engine keeps changing things. So I want to thank all of you in the room for continuously showing me support, and let's keep moving forward. Let's make lunar simulations even better tomorrow. Thank you.
Thank you for the very interesting talk. One quick question. So I will ask, what's the last or the most challenging thing on your way to moon, actually? What is the biggest thing you still need to do, besides getting funding and right, of course?
The easy answer is money, but I think grounding ourselves to actually understanding the real challenges, because we look at it from afar and everything seems easy, but the more you dig in, you realize that even the minute details you don't consider every day have such a big impact on your possibility of success on the actual mission. So we have to temper expectations while also be scientifically accurate. I think that's the biggest challenge with the new generation.
Okay, thank you.
Thank you.
Yeah, next talk, Yehor Surkov will be mapping Olivine on the moon. Please. Okay, all the lunar rover team goes. They just want to drive a rover, but they don't want actually to investigate the moon, what is it made of, and so on. They just want to drive. No, yeah. Engineers.
Okay. Before every presentation, we saw my first slide, and it's on the screen. It's okay. It's okay. So it's probably the most well-advertised thing. So I am Yegor Surkov from the University of Helsinki, and as was mentioned, today we will speak about the olivine mapping on the Tsiolkovsky crater region and several aspects of the spatial and spectral resolutions. So olivine is one of the main rock-forming silicate mineral. It's quite abundant on the mantle-derived rocks, and has been considered solidified quite deep into the lunar interior. Its surface exposures carries important information about the, for example, composition of lunar interiors, as well as some aspects of the processes which uplifted the olivine into the surface. Fortunately for the remote sensing, olivine has quite prominent spectral features in visible and near infrared spectral range. It has quite prominent and asymmetric absorption broadband near 1 micron and almost completely depleted absorption band near 2 microns. And combination of these factors actually opens a window of possibilities to get some idea of the quantitative numbers of abundance of olivine in the lunar regolith. However, this parameter, retrieving these integrated band depths, is quite demanding for the technical properties of the devices, and for now only one data set is capable to construct the decent maps for the olivine abundance. It's Chandrayaan-1 M-Cube data. However, this data set has lacks in terms of spatial resolution, which we aim to restore using the another data set from Kaguya multi-band imager, which has much poorer spectra, whereas it has more than 10 times higher spatial resolution. In order to do this, we want to explore the capabilities of artificial neural networks to establish the correlation between the spectral parameters that we can retrieve using the Kaguya MI data and as an output to get something that is olivine abundance. As a training data set, we use the carefully registered olivine map from the Chandrayaan-1 and registered with the MI Kaguya data from which we can retrieve the input parameters. And to show you how it works, for example, here I present several spectra that are tiered according to the olivine abundance. These olivine abundance are predicted with the neural net after the training, and if we have got quite abundant olivine, everything is okay. These spectra are quite asymmetric with this efficient excess of the absorption near 1.2 microns. However, where the neural networks provide us some benefits, it's where the olivine is less abundant. For example, it allows us to discriminate spectra with quite broad but symmetric band from pyroxenes, or with very, very shallow band that resembles olivine, however, probably of pure anorthosite. So it's quite hard to achieve using the more, let's say, conventional statistical methods. Now we can actually go to characterize our olivine deposits on the Tsiolkovsky crater. Here we can see from the first glance that olivine is distributed between two distinct units. One is a smooth, moderately olivine-bearing basaltic floor that is actually quite common for lunar basalts. Probably the one strange thing here that Tsiolkovsky crater placed on the far side of the moon with quite thick crust. This is not that big crater, 200 kilometers, and it means that there is some process before, probably this South Pole Aitken impact that brings a bit closer to the surface this olivine. But what's even more interesting that we observed highly patchy olivine reach up to 70 volumetric percent units on the top of the crater peak. And we can check the spectra from the M-cube that really they reveal quite proliferant olivine feature and does not reveal any other feature. What's even more interesting, that unlike these olivine deposits on the crater floor, these deposits of the crater peak correlates quite well with the rock abundance. Thanks to Anna, I do not need to introduce this parameter again. I just show this picture that if we have got quite high values of rock abundance, we definitely can find quite heavy bouldered area. And this looks quite interesting, especially that not all boulders have a lot of olivines, but a lot of boulders have quite abundant olivines. Probably we can speak even of donitic origin. Here I would like to present more clearly the super resolution effect that we achieved if we check these very, very patchy deposits with these two tongues of smooth dark materials. We can see that this rock abundance, which has special resolution about the 200 meter per pixel, cannot resolve actually these tongues, whereas the olivine M-cube parameter, or this merged parameter, really is highly associated with the most bouldered regions, which is very interesting actually. And what we can do else, we can check the vertical distribution of our olivine on the peak, and we can see that actually the topmost part of the peak presents the higher abundance of olivine. Most of the lane below's surface exposures of olivine are either can be connected to the secondary peaks or can be connected with the landslides from the top. It actually means probably that as according to the current views on the crater formation, the crater peak represents actually inverse stratigraphy. So the deepest layers from which the material uplifted during the impact should be placed on the topmost part of the peak. So if it's like this, we have got this opportunity studying separately these boulders and see them as the deepest material that we can reach, that are available currently for the remote sensing investigation. So, coming to the conclusion, the proposed simple INN-based data fusion approach enables super resolution of olivine mapping. Here I must tell that this is very highly specific procedure, and some efforts must be applied before it can be generalized. It's not that easy just to, for example, create two outputs. Usually one output will be fine, and another output, for example, pyroxenes, will be identified much poorer. Then up to the Tsiolkovsky crater, here we found two types of olivine occurrence, just a moderately enriched and more or less homogeneous basaltic units, and highly olivine-rich patchy deposits on the topmost part of the central peak, where it is associated systematically with the boulder-rich terrains. And as a perspective of future work, we can actually see that olivine is not a monolithic chemical composition. It has some variations, and these variations still provide the same main features. However, they are different in more specific parts of the spectral profile of olivine. And actually now, if we identify these boulders of very, very deep material, we can try to associate it with other data, spectral data of point lunar spectrometers like SEER-2 on board Chandrayaan-1 as well. These point spectrometers usually have much better spectral capabilities, which further allow to characterize and constrain the composition of olivine. Thank you for attention.
Thank you, Jehor. We have time for questions. I still see some people from the Coop Kulgur team who must be project scientists, right? Any question?
Thank you. Nice presentation, Igor. Could you show this slide with a number of spectra? Yeah, this one. What is the difference? Is it the content of iron?
Yes, mostly the content of iron, but also at some spectra we can see probably some chrome, and some chrome can sit here as well. Olivine, actually, yes, it has two end members, but there are some additions.
Yeah, but if we consider first right and firelight, where it is on the bottom firelight? Or
Yes.
Okay.
And within the group of firelights, there are also some accessory subdivisions according to the accessory amount of other cations.
Is it laboratory measurements?
Yes, it's laboratory measurements.
Because there are also laboratory measurements of refractive indices of different types of olivines. Glasses, basically.
Glasses or olivines? Crystalline phase or glass phase?
No, glass.
Glass, okay.
So they used basically in cometary science. So I'm just wondering, I don't recall much absorption at 1 micron there. It looks like...
For glass, it also should be some absorption.
Yeah. Okay.
What was the question?
No, I was just trying to figure out where is how these figures change with content of iron. I see that from top to bottom.
If you're interested, I can send you another figure which it's explicitly stated.
Okay.
It's not about the content of iron, it's about the diversity olivine in general.
Okay, thank you.
Yeah, pure forsterite being magnesium rich end member would have no absorption because the absorption is due to Fe2+. And the position is due to if the Fe2+ is in 1 or a second crystalline position, M1 or M2 side of the silicate tetrahedra. But yes, in general, with increasing iron content, you deepen it and you also shift the position of the minimum. And if you have glass, it's more amorphous, so it would get broader and less shallow because it loses the crystalline structure. Ideal glass would not have possibly any absorption.
Hopefully we almost never have this ideal glass and certain close crystalline structure still preserved.
It has effect on the position of the minimum and the strength of the band. As more iron, it's better. Yes. I have a question. So you use different minerals from mineral databases to train your algorithm for the abundance. What do you use to train it for the super resolution?
So to retrieve this, I used different spectra from the RELAP database. And then to achieve super resolution, I took the olivine retrieved from the M-cube data. Then I squeeze into the M-cube resolution, so I lower the resolution of the MI Kaguya. I spent a lot of painful time to merge it with the M-cube data. Then I have got a set of Kaguya data in the coordinate system of the M-cube data. From this data set, I can retrieve this parameter as an input. From M-cube, I have got the olivine abundance for output. And this is my basically training set. Actually, I trained this with a Copernicus crater, so Tsiolkovsky crater is a blind experiment. Copernicus crater here, occurrence of olivine is very well studied, and it's believed one of the broadest, broadest variation of the olivine content, or this.
Okay, thank you. So let's thank the speaker again. And last talk, Gabriel Schwarzkopf, Venus emissivity mapper.
Yeah, it works. Hi, yeah, so I'm Gabriel, and I'm going to present the Venus emissivity mapper, which we're building in DLR in Berlin. And I'm especially going to talk about the current status and detector qualification. And what's maybe interesting to know about the instrument is that we're actually going to use it on an ESA and on a NASA mission. So it's going to be on the ESA Envision and on a NASA Veritas mission, or JPL Veritas mission. To give you a quick overview of the mission, then I'm going to quickly talk about the science objective to give a little bit of background, then the instrument, a little bit of the requirement flow down, because that gets a bit more interesting when you have two different organizations from two different continents that give you input, let's say. Then, as I said, detector qualification, and afterwards a little bit about the instrument design itself and the current state of that. All right, so why do we go to Venus? Basically, there is a whole revival of the Venus topic, many missions going there because it's very Earth-like, but we know that it was very Earth-like, but it's not anymore, as we know. So what we try to do is what happened to Venus. We want to understand what happened to Venus and why is Earth the way it is right now and Venus the way it is right now. And we're especially trying to combine the data, in our case, by mapping the surface in a surface spectra, and to map the change on the surface. What are the science objectives? Well, we want to understand the surface rock composition, to understand the general setup of the surface of Venus, and try to understand if there is similar processes or similar features on Venus like on Earth. Most prominently, does it have a continental crust, sort of like on Earth? Then there's also going more into detail. I'm not a scientist, so I don't know the details very much, but going into detail about the composition of all the rocks on the surface or all the boulders, and to reduce basically the uncertainties that are there in the current data, which is also not very much, actually, since the Venus hasn't been studied for long. To give a quick overview of the instrument design, so as I said, it's a multispectral imager. The range is basically in the near-infrared rather, so it's in the 790 to 1500 nanometer range. It's an in-gas detector, which is cooled down by the spacecraft in the end. And for protective measures, we have a single-shot mechanism to protect it from the atmosphere at Venus, because there will be aerobraking in both Envision and Veritas. So during that time, we want to have simply a protective layer in front of the optics. And on the other side, we also can use it as a contamination shield, basically during integration. Then there is the electronic box with power supply and the instrument controller. And of course, as with every telescope, there's a cone and a baffle, and the whole FBA. The current status, so last year, or at the end of last year, we passed the PDRs. So PDR of Veritas was in June, and we passed it, and then Envision it was the September, October, December, November timeframe. And so we're now going into the detailed design. We're trying to keep both, as you see by that, we're trying to keep both missions on sort of similar time scale. Also the launch dates, for the people that don't know it, have aligned to very large extents now, so both missions intend to launch in 2031. We have our first prototypes available, so hardware prototypes available, and the software development started. And we're also trying to work on a virtual instrument, so as has been said before, also basically a digital twin of sorts, which is just doing functional emulation of the mostly of the CPU actually on the control hardware, not the actual entire spectrometer. Now a bit about the requirements flow down. So as I said, we have an instrument that's being basically flown on an ESA and a NASA mission. So we get requirements from ESA and from NASA. They align in some cases, they don't very much align in other cases. So what we're generally trying to do is, what we did actually for PDR, we went into the science requirements from both sides, we went into lower level requirements like ICDs or environmental requirements, which in the ESA case is covered in the EIDA requirements document. And from that we try to derive basically a single technical requirement document for our instrument, and we try to envelope more or less the requirements from both missions to have, in the best case, a single design for both missions, which is working quite well so far. But of course there's some few cases where we have a direct flow down into, let's say, mission-specific documents in the end, where it simply does not make sense to take over the requirement from one
let's say, organization to the other, because it's very, very specific. But in the end, of course, what we present to ESA, or what we did present to ESA and NASA in both cases, is also then a mission-specific document. Yeah, because of the deviation that still exists, but we try to keep it very, very small. Then we went to detector qualification. So the detector we're going to use now is actually not space qualified. So most importantly, what we needed to qualify is actually for the radiation environment. And we did, so that's the tie to Finland actually, we did heavy ion testing for the single event upsets or single event effects here in Radev in Jyväskylä. It was performed at that time at 10 degrees. We had a small setup where we basically had the detector and our readout electronics, or simple readout electronics. And the most positive thing in the beginning is that the detector survived the test. That's very good already. But it showed some sensitivity to heavy ions. We afterwards implemented a lead shot protection because we saw that there is heavy ion, there's a sensitivity to heavy ions, but generally we still see that statistically speaking in a normal year we would only assume one, or we get to one lead shot actually for the entire 5-year mission at Venus, or in the flight to there. What we also saw is a dark current increase, and the most common event that we saw, so the most error that we saw, is actually sudden increase in single pixel luminosity, which makes sense from let's say a physical perspective, but no permanent degradation, and that was actually the most important outcome that we wanted to see. And here is an example of the sudden increase in luminosity, which basically just shows, okay, there is sort of a how to say it, like a flash and then it's gone again, which is the impact of some heavy ion, of course. Then that was a bit closer, directly on campus, basically in Berlin. We could also do the total ionizing dose tests, where it also showed, luckily, the sensor a very good performance. It was robust, and we had, in the live images that we had a look at, there was no corruption, but there we saw some dark current increase and also an increase in readout noise, but was not significant, luckily. What was more interesting was the random telegraph noise that was introduced. So generally we see generally we see from prior test picture to after the test, we see quite an increase here, or it's very clearly visible, but annealing actually allowed to decrease that effect quite a bit again. So that's also good to know. Sorry, I have to drink something quickly. All right. So yeah, with annealing, we were able to reduce the effect again, which was also results why we introduced annealing as an option, at least for now, or into the baseline, let's say, for the PDRs. Then let's go into the electrical architecture. We have basically 4 main subsystems, electrically speaking, which is the power supply, the instrument controller, which I'm going to talk about a little more in just a minute, and the analog electronics, which is close to the detector, and for our turn window unit, so the only one-shot mechanism that I said before, the turn window unit is basically the cover. We have a dedicated electronics unit for basically, so it works via heating up a resistor, and to have a control electronics for this resistor, we have a separate board. Most importantly, maybe for the instrument controller, we have an NG medium that's sort of a given from ESA, and we have that we are using it, and we're running a Leon 3 on it. The only difference that we so far have, electrically speaking, between the 2 missions is actually that for so this is the Veritas configuration. We have a dedicated link, which is also redundant again, for the scientific data. And for the Envision mission, we actually have a combined link for housekeeping, telemetry, and science data. So there's only 2 links. Otherwise, the design is exactly the same for both missions still. Looking into the software, we're trying, so this is my field of expertise more, we're trying to keep a single software or a single software program, let's say, for both missions, which is also looking good so far.
but it consists in principle of a small boot software, which cannot be upgraded in flight anymore. We can upgrade it on ground still, because it's part of the FPGA design, but not in flight anymore, which is why the verification is critical and why we keep it very, very small. And then we have the application software, which is basically the science processing and the control of the instrument during nominal science operations, but that can be upgraded during flight. In both cases, we decided on a cooperative scheduler, so there is no RTOS, at least right now, in the design intended, for a very simple reason, because our software is actually driven by the hardware. So the FPGA basically does most of the data processing because of the bandwidth of the memory. So what we realized is that the external memory is actually quite slow from a bandwidth perspective, unfortunately. So actually when we read out the sensor, it more or less blocks access from the software to the external memory, so the big storage memory. So we basically had in that for several milliseconds every acquisition, which means we have to sort of build around this entire fact, the software. So in total, the entire software design is basically driven simply by these hardware effects now. And otherwise, we're keeping a static memory layout because any, let's say, dynamic memory layout is, of course, much more complicated to validate. Then we have the onboard data processing. Of course, it starts with the image acquisition of the sensor. We then do signal weighting for the different pixels. We have time-delayed integration and binning, and then we do a lossless compression. Again, all in the FPGA, that's at least the current baseline. Potentially the image compression goes into the CPU, but we will have to see. And of course, we're doing some dark measurement as reference simply. So dark frames where we look into deep space effectively. Yeah. This is in the end shown as a sort of graph here. And maybe one peculiar thing, so both missions are in a non-circular orbit, at least in the beginning of the mission around Venus. And to meet our science requirements with a given ground sampling distance, we sort of have to variate several parameters across along the orbit because it's not a circular orbit, the ground sampling distance constantly changes, so we need to adapt the binning parameter to still meet our science requirements. That also gives us some challenge because we of course cannot actively command the instrument while it's around Venus, so we need to think about how to timeline this properly in advance. So in conclusion, we're trying to do a design for a single instrument for 2 missions. So far it's looking good. So far it seems we can really work with basically a single design with very, very minor variations. We're keeping still, at least for the software, especially a single requirements baseline. It was challenging to qualify the detector because we couldn't use a already qualified one, but it still looks good. So it succeeded so far, and it's accepted from ESA and NASA after PDR. The software is unfortunately driven very much by the hardware, so we have a lot of constraints that we now need to take into account because of the bandwidth issue that we discovered. But generally speaking, that's why the processing has moved more and more into the FPGA. All right, that's it.
Thank you. Questions?
Yeah, let me just formulate this. Where do the requirements diverge the most? Or I mean, there are obviously a few places, but for example, like operations, interface, just standards.
So operations right now is in both missions not too clear yet or not too strictly defined yet, let's say. And also the scientists in the end decide also, of course, of how operations is going. So there we are still pretty similar, but there's also not very strictly defined yet. The biggest difference that we actually know right now is, in fact, the difference of the hardware interfaces. So we have spacewire interfaces here. And for example, in the software, I mean, in the hardware, it means there cannot be a physical interface, of course. And in the software, it means we basically have a adaptable software in that part where during boot up, it basically checks is there an interface or not. So that's a small difference, but we try to keep still the same code. So we can use the verification campaign because, of course, if you would have two different compiled software products in the end, this would mean you have two different verification campaigns, very generally speaking. So that's one point. Of course, the whole environmental test campaign is a little bit different because ESA and NASA have different standards, and you simply they simply put different focus. It's not that one is better than the other or anything. It's really just they keep different focus, and that's why we do sort of a envelope qualification, and we're always showing to both parties this is the envelope of both sides, and also explain why are we doing, for example, sometimes an overqualification for the one agency, which is simply driven by the other agency having a focus on that one, and vice versa. And that exists actually in both directions. So there's not one that has higher requirements than the others or anything. So
just really quickly, do you think it has any benefit? Like, do you think you get a better instrument from this kind of challenge?
I think in the end, yes. So the advantage is actually that we have a review from experts from Europe and from the US simply. So it's just more people reviewing it. On the downside, that of course means also more work for us because there's more people looking and you have to explain sometimes the same things again and again. So as everything, it has advantages and disadvantages. In the end, I think there will be less surprises with the final product. Let's put it like that.
Thank you, Gabriel. First question is like, how big is your team?
So for the entire instrument, you mean?
Yeah.
I cannot even tell right now. I would assume maybe 25 people, that order of magnitude at least. I would need to start counting. I don't want to do that right now, but I like that order of magnitude. So since I'm doing mostly software, for software alone, it's nearly 10 people. They're not all working full-time, so it's a bit hard to... How do you count those people? But yeah, I would say 25 to 30 people.
Second question is, which people are the hardest to find in your team? Like, is it also FPGA?
Optical engineers, actually.
Optical?
Yeah, we have a long-standing FPGA expert, which is a good advantage for us. And he has a lot of experience, which is an even more important advantage with FPGA design. But optical engineers, so we also have one, but that's sort of like, it's harder to find another optical engineer that's good. And I mean, as you can see, the optical design for such instruments, I mean, all of this here, effectively, this is lens after lens after lens after filter after lens. Optical design is quite complicated, actually. And it's, yeah, you need somebody good to bring it in such a compact format that works in a space mission. That's actually the thing. So generally optics is potentially a bit easier, but you need to fit it in a small instrument and make it lightweight, and that's where it gets tough in the optics. So yeah, I would say that's actually the biggest challenge.
Thank you.
You're welcome. Now it escalated into work.
Okay, then I will just ask this question.
Oh, yeah.
So and by the way, it's a two-part question. So
yeah.
The first part is we have two missions. So what is the time between the launch dates?
I actually don't know it right now anymore because especially the Veritas at the NASA side shifted quite a bit because of, I guess, very known budget discussions, let's put it like the least. But right now they actually aligned both to 2031. I don't know how far they are apart in year 2031, but they're actually expected to launch in the same year by now. Originally Veritas was earlier, but as I said, budget problems, so they kept postponing it. And now it's both in 2031 because you also for Windows you can launch anytime, so you have certain launch windows. They're more often than for Mars, for example, but still you have certain given launch windows.
Well, okay. The other part of the question was if you have an issue with the other mission, so do you have the opportunity to take the lessons learned into account? But if they are launched in the same year, I think the answer is no. But
unfortunately, no. So it will become now a little bit. So that was actually the advantage in the beginning that we would have had if one which was, as I said, the Veritas mission, we would have had sort of we had a clear pipeline of which model to build when with the flight models. Now this is of course not as clear anymore because they sort of would need to be ready at the same time, but of course we don't have the facility, so we actually still need to be ready earlier for either one of the missions for sure. And start, let's say, integrating the flight models comparatively early, because we have to build in total actually 3 flight models. So for Veritas we have 2 times them on board, and on Envision we have it 1. So actually we have 3 flight models plus then spare parts that we still, or spare components that we need to manufacture.
Okay, because I was appointed chairman, so I will end this session.
All right, thanks everyone.